What if the moon isn't just a lifeless rock orbiting Earth, but an alien observation station watching everything we do? For decades, one controversial theory has claimed that the moon could contain a hidden extraterrestrial base, advanced technology, or even structures designed to monitor humanity. Supporters point to strange lunar anomalies, mysterious lights, unusual formations, and questions surrounding the moon's incredible properties. But are these genuine clues, or are we simply seeing mysteries where there are scientific explanations? And if an alien civilization really was watching Earth from the moon, would we even know? In this video, we investigate the moon base theory and uncover the strange claims behind one of the most fascinating lunar mysteries. Every night, 250,000 miles away, something hangs in the sky that we have stopped questioning. It rises without sound. It pulls the oceans back and forth twice a day with a force we feel but rarely notice. It has watched every human being who has ever lived, and every one of us has watched it back. And somewhere in that mutual staring contest, we decided we understood it. We do not. Not really. We have walked on it, drilled into it, bounced lasers off mirrors left on its surface, and flown spacecraft into orbit around every square mile of it. And after all of that, the honest answer to the question, what is the moon and why is it there, is far less settled than most people assume. This series exists inside that gap between confidence and evidence. It is built around one question, asked plainly, without apology. Is it possible that the moon is not simply a dead rock that happened to end up circling our planet, but something placed there, shaped there, or used there by an intelligence that was not human? That question sounds, on its face, like the premise of a science fiction film, and to be clear from the outset, this series does not claim to have proof that aliens built or occupy the moon. No one has that proof. What this series does have, and what it intends to walk through carefully, part by part, is a body of genuine anomalies, documented data, and unresolved scientific puzzles that have accumulated over more than half a century of lunar exploration, alongside the specific hypothesis, advanced by credentialed scientists and taken seriously enough to be published and debated, that the moon's structure, behavior, and even its very existence in orbit around Earth cannot be fully explained by natural processes alone. Whether that gap in explanation points toward an artificial origin, an engineered structure, or simply the limits of our current models is a question this series will let you answer for yourself. Our job is to lay every piece on the table. Consider for a moment what a genuinely natural moon should look like. Most moons in our solar system are captured objects, chunks of rock and ice that drifted too close to a planet's gravity well and got trapped in orbit. They tend to be irregular in shape, often only a few dozen or a few hundred miles across, and their orbits are frequently eccentric, tilted, or unstable over long timescales. Mars has two such moons, Phobos and Deimos, small lumpy rocks that look exactly like what captured asteroids should look like. Our moon looks like nothing else in the solar system. It is enormous relative to its parent planet, more than a quarter of Earth's diameter, a ratio found nowhere else among the rocky planets. Every other moon-to-planet size ratio in the inner solar system is a small fraction of ours. Pluto and its moon Charon come closer to matching that kind of ratio, and even the International Astronomical Union has occasionally discussed whether that pair should be considered a double planet rather than a planet and a moon. Earth and its moon sit in strange company, and size is only the beginning of the strangeness. The moon's orbit is nearly circular, its orbital plane is oddly aligned, and its rotation is locked to its revolution so precisely that it always shows Earth the same face. Tidal locking itself is not unusual. It happens to many moons over enough time as gravity grinds their rotation down to match their orbit. What is unusual is the specific geometry that results from the moon's size and distance from Earth. The moon's diameter is about 400 times smaller than the sun's. The moon also happens to sit almost exactly 400 times closer to Earth than the sun does. The result of that coincidence is that from our vantage point on Earth's surface, the moon and the sun appear to be almost precisely the same size in the sky. That is why total solar eclipses look the way they do, with the moon's disk fitting almost exactly over the sun's, leaving only the delicate corona visible around the edges. No other planet in the solar system, as far as we have observed, has a moon that produces that kind of exact optical fit with its star. Mathematicians and astronomers who have looked at this coincidence describe it correctly as an accident of orbital mechanics, the kind of thing that can happen given enough moons and enough time across a vast universe. Others look at the same numbers and ask a quieter, more uncomfortable question. What are the actual odds, and are we simply the one civilization lucky enough, or perhaps engineered enough, to witness it? The coincidences do not stop with eclipses. The moon's rotation is locked so precisely to its orbit that from Earth, we only ever see one hemisphere, the so-called near side, while the far side remained completely unseen by any human eye until a Soviet probe photographed it in 1959. A slight wobble called libration lets us glimpse a little more than half of the surface over time, roughly 59%. But the remaining portion stayed a total blank on every human map for the entire span of civilization until the middle of the 20th century. Tidal locking is common enough among moons across the solar system that it is not, by itself, unusual. What some researchers find harder to dismiss is the layering of coincidences on top of one another. A moon large enough to stabilize a planet's axis, positioned at a distance that produces a flawless solar eclipse, locked in rotation so that one face is permanently hidden from the world it orbits. Any one of these facts alone is unremarkable. Stacked together, they form the foundation of an argument that has never fully gone away, no matter how many times it has been set aside by mainstream astronomy. That eclipse geometry is only the entry point. Once you start looking closely at the numbers, more of them line up in ways that feel less like coincidence and more like design, at least on the surface. The moon is receding from Earth by about 1.5 inches every year, a measurable drift confirmed by the retroreflectors left on the lunar surface during the Apollo missions, which allow scientists on Earth to bounce laser beams off the moon and measure the distance with startling precision. Run that recession backward across geological time, and the numbers get strange fast. At various points in Earth's deep past, the moon would have been close enough and large enough in the sky to trigger tidal forces on Earth so extreme that many scientists consider it a serious factor in why complex life took the shape it did, why the oceans behave as they do, why Earth's rotational axis has remained tilted at a stable angle for billions of years, instead of wobbling chaotically the way Mars's axis is believed to have done in the absence of a large, stabilizing moon. Take the moon away, and Earth's climate, tides, and even the length of our day would be radically different. Some planetary scientists have gone so far as to argue that a moon like ours may be a near requirement for a planet to develop and sustain complex life at all. If that argument holds any water, then the object hanging over your head tonight is not a passive companion. It may be one of the load-bearing pillars of your own existence. And that raises the next question naturally. If something is that important to the development of life on Earth, is it truly plausible that its presence, its size, its distance, and its orbit are the product of pure chance? This is where the mainstream account and the alternative account begin to diverge, and it is worth being honest about both from the very first part of this series. The mainstream account, and it should be said clearly that this is the position held by the overwhelming majority of planetary scientists, is called the giant impact hypothesis. It proposes that roughly 4.5 billion years ago, in the violent early days of the solar system, a Mars-sized protoplanet, often given the name Theia, collided with the young Earth at a glancing angle. The impact was catastrophic, vaporizing part of both worlds and flinging a ring of debris into orbit around the newly reformed Earth. That debris, over a relatively short span of time, geologically speaking, coalesced under its own gravity into the moon we see today. This hypothesis explains a great deal. It explains why lunar rock samples share striking similarities with Earth's mantle composition. It explains why the moon has a small iron core relative to its size, consistent with forming from material that had already been stripped of much of Earth's heavier iron. It has become, since the 1980s, the dominant scientific consensus, and we will spend an entire part of this series later on walking through it in detail, along with the genuine problems that continue to trouble it, even among scientists who accept it as the best available model. Because it does have problems, real ones, published in peer-reviewed journals, not manufactured by conspiracy theorists, the isotopic ratios in lunar rock samples are, in places, almost too similar to Earth's, more similar than most impact simulations predict they should be if the moon formed mostly from Thea's material rather than Earth's own. The angular momentum of the Earth-Moon system doesn't cleanly match what a single glancing impact should produce, and the moon's overall density, its internal structure, and the distribution of mass beneath its surface contain irregularities that have never been fully resolved, irregularities we will spend significant time on later in this series because they form the backbone of the more radical hypothesis that gives this documentary its title. That hypothesis has a name, or rather several names depending on who is telling the story. The spaceship moon hypothesis, the artificial satellite hypothesis, or, as we'll refer to it throughout this series, the observation station hypothesis. In its strongest form, it proposes that the moon is not a naturally accreted body at all, but either an artificially constructed object, a hollowed and modified natural body repurposed by an advanced intelligence, or an installation placed into orbit around Earth for the specific purpose of observing the development of life and later civilization on the planet below. This idea did not originate with internet forums or late-night radio callers, though it has certainly flourished in both of those spaces over the decades. It has a documented history, one that traces back to a peer-reviewed adjacent 1970 paper written by two Soviet engineers, Mikhail Vasin and Alexander Sherbakov, published under the title, "Is the Moon the Creation of Alien Intelligence?" in the Soviet popular science journal Sputnik. We will examine that paper in detail in a later part of this series, including exactly what evidence they cited and how the scientific community responded to it, both at the time and in the decades since. For now, it is enough to know that the idea has a real intellectual paper trail, written by people with legitimate scientific and engineering backgrounds, working within the Soviet space program's own orbit of expertise, not fringe amateurs disconnected from the field. The idea did not stay confined to a Soviet science journal. 5 years later, in 1975, an American researcher named Don Wilson published a book titled Our Mysterious Spaceship Moon, which took the Vasin-Sherbakov argument, combined it with newly released NASA data from the Apollo program, and delivered it to a much wider English-speaking audience. Wilson's book leaned heavily on the same seismic ringing data we mentioned a moment ago, on measurements of the moon's unexpectedly low average density compared to Earth, and on the discovery, made by NASA's own lunar orbiter missions in the mid-1960s, of dense, localized concentrations of mass beneath several of the moon's impact basins, features that came to be known as mascons, short for mass concentrations. Wilson argued that the pattern of these mascons, sitting beneath circular Maria in a way that seemed too regular to be coincidental, was consistent with buried structural elements rather than simple pools of solidified lava. NASA's own scientists, working from the same data, reached a very different conclusion, one we will examine in full later in this series, but the fact remains that the raw measurements Wilson was working from were never in dispute. The disagreement was, and still is, entirely about interpretation, not about whether the data itself is real. That pattern, real data paired with disputed interpretation, is one you will see again and again throughout this series, and it is worth naming clearly here at the outset so you can watch for it as we go. Almost nothing in this documentary rests on data that NASA, the Soviet space program, or any other space agency has denied collecting. What is contested consistently and often heatedly is what that data means, and whether the conventional explanation offered for it is the most complete one available, or simply the most convenient one for a scientific establishment that has a great deal invested, institutionally and psychologically, in the idea that the moon is exactly what it appears to be. It also helps to understand who Vasin and Shcherbakov actually were, because their professional backgrounds are frequently misrepresented in both directions, either inflated into official Soviet government scientists making a state declaration, or dismissed as science fiction writers with no real technical grounding. Neither description is accurate. Both men held engineering credentials and worked in fields adjacent to the Soviet space and defense industries, publishing their argument not as a peer-reviewed academic paper in the formal sense, but as a long-form feature in Sputnik, a magazine that at the time functioned as a Soviet equivalent to Reader's Digest, translating and summarizing Soviet scientific and cultural writing for a general audience. That distinction matters. It means the piece was subject to editorial review and was taken seriously enough to be commissioned and published by a state-sanctioned outlet, but it did not go through the same peer review gauntlet that a submission to a geophysics journal would face today. That places it in an unusual middle category, more substantive than a blog post or a rumor, but short of the rigorous adversarial review that separates an accepted scientific finding from an interesting hypothesis. We mention this not to discredit the paper, but because an honest series has to be precise about the actual weight any given piece of evidence can bear, and precision is something this genre of documentary does not always prioritize. What gave that 1970 paper its staying power, and what continues to give the broader hypothesis its staying power today, is that it did not invent its evidence out of nothing. It pointed to real data collected by real space agencies, data that in some cases remains only partially explained even now, more than half a century later. Chief among that evidence, and the subject we will devote an entire part of this series to, is what happened on November 20th, 1969, when the ascent stage of the Apollo 12 lunar module was deliberately crashed into the moon's surface after the astronauts returned to orbit, a standard part of the mission's seismic testing program. Instruments left behind by the astronauts recorded the resulting vibrations, and what they recorded surprised the scientists monitoring the data back on Earth. The moon did not simply absorb the impact and go still the way a solid rock should. It reverberated, it rang. The vibrations continued, gradually diminishing for close to an hour. NASA's own scientists, not conspiracy researchers, used the word ringing in their technical descriptions of the event, and the phenomenon was significant enough that it was repeated deliberately in later Apollo missions, with even more dramatic results, to gather more data on what was producing it. We will walk through exactly what NASA's seismologists concluded about that ringing, what it does and does not tell us about the moon's internal structure, and why the phrase, "the moon rings like a bell," escaped the world of academic geophysics and entered popular culture as one of the most frequently cited pieces of evidence for an artificial or hollow moon. That is the shape of this series. We are not going to simply assert that the moon is an alien space station and move on. We are going to build the case the way an investigator builds a case, piece by piece, source by source, starting with the ancient human relationship with the moon and moving forward through the history of lunar science, the Apollo program, the seismic data, the hollow moon hypothesis in its full technical detail, the strange transient lights that observers have reported on the lunar surface for centuries, the photographic anomalies pulled from NASA's own archives, the far side of the moon that Earth never sees and that only became visible to human eyes in 1959, the public statements and later remarks made by the astronauts who actually went there, the specific claims of artificial geometry and structures that have circulated since the 1960s, the unsettling mathematics of the moon's orbit and and size, the parallel and sometimes corroborating claims to emerge from Soviet and Chinese lunar missions, and the culture of secrecy and classification that surrounded the entire space race, and that continues, in more limited form, around lunar and planetary science to this day. And when all of that has been laid out, we are going to do something that a great many documentaries on this subject choose not to do. We are going to give the skeptics their full say. An entire part of this series is reserved for the mainstream scientific rebuttal, point by point, claim by claim, because a fair examination of an extraordinary hypothesis has to include the strongest version of the counterargument, not a straw man. The seismic ringing has a proposed geophysical explanation involving the moon's dry, fractured, and nearly waterless crust, which transmits vibration very differently than Earth's wet, layered crust does. The mascons, the dense mass concentrations beneath the lunar surface that some point to as evidence of buried structures, have a proposed explanation involving ancient basaltic lava flows filling in impact basins. The transient lunar phenomena, the flashes and glows reported by astronomers for centuries, have proposed explanations involving outgassing, meteorite impacts, and even the physiological effects of staring at a bright object through imperfect optics. Every claim in this series has a mainstream counterclaim, and by the end, you will have heard both in full, not filtered through the assumptions of either side. Why does this matter? Why spend hours of runtime on a hypothesis that the majority of working planetary scientists do not accept? Because the history of science is, in no small part, a history of hypotheses that started as fringe ideas and were later vindicated by better data, sitting alongside a much larger number of fringe ideas that were investigated seriously and were, in the end, simply wrong. Continental drift was mocked for decades before plate tectonics vindicated it. The idea that a giant asteroid impact wiped out the dinosaurs was dismissed by much of the paleontological establishment when it was first proposed in 1980, until the discovery of the Chicxulub crater brought the scientific community around within about a decade. The geologist Alfred Wegener faced a similar wall of institutional resistance when he proposed continental drift in 1912, ridiculed for decades by a geological establishment that had no mechanism to explain how continents could possibly move, until the discovery of seafloor spreading in the 1960s supplied the missing mechanism and vindicated an idea that had been treated for most of its life as an embarrassment. Neither of those examples proves that every fringe hypothesis deserves equal weight with settled science, and this series will not pretend that they do. Most fringe ideas remain fringe because they are wrong, not because they are secretly correct and merely unpopular. But the Wegener and Alvarez cases do illustrate why an idea's popularity, or lack of it, among credentialed experts at any given moment is not by itself a reliable predictor of whether that idea is ultimately correct. Sometimes the outsiders are cranks. Sometimes they are early. The only way to tell the difference is to look at the actual evidence carefully and see where it leads, which is exactly the discipline this series is attempting to hold itself to across every part that follows. It is worth being explicit here at the start about the standard of evidence this series is going to hold itself to, because a documentary that promises to take a fringe hypothesis seriously owes its audience some clarity about what seriously actually means. It does not mean uncritical acceptance. Every claim presented in this series as evidence for the observation station hypothesis will be sourced to something concrete: a NASA technical report, a peer-reviewed geophysics paper, a published mission transcript, an on-the-record statement, or a named published work like the Vasin-Shcherbakov paper or Wilson's book. Claims that circulate widely online but cannot be traced back to an actual document, mission record, or named source will be identified as such, or left out entirely. And as already promised, every major claim will be paired, later in this series, with the strongest mainstream explanation available for it. That is not a hedge or a disclaimer inserted to satisfy network lawyers. It is the only honest way to examine a question this contested, and it is the approach this series will hold to from this first part all the way through to the last. This is also not simply a historical curiosity revisited for nostalgia's sake. Humanity is returning to the moon in a way it has not since the final Apollo mission left the surface in December of 1972. NASA's Artemis program is actively working towards sustained human presence near the lunar South Pole. China's Chang'e program has already landed spacecraft on the far side, the hemisphere that stayed hidden from every human eye until 1959, and has returned samples from regions of the moon that Apollo never touched. India's Chandrayaan missions have mapped water ice in permanently shadowed craters. Private companies are contracting with space agencies to land instruments and, eventually, crews. Every one of these programs is generating new data at a volume and resolution the Apollo-era scientists could not have imagined, and every one of them is, whether intentionally or not, revisiting the exact regions and questions that generated the original anomalies decades ago. If the observation station hypothesis is wrong, this new wave of exploration should be the very thing that finally puts it to rest, filling in the gaps in our knowledge with hard, uncontestable data. If any part of it is right, this is also the moment when that evidence would be hardest to keep quiet, spread as it now is across multiple space agencies, private companies, and countries that do not answer to each other. That tension between a scientific community confident the mystery is already solved and a body of unresolved data that keeps resurfacing with every new mission is part of why this question has outlived the era that first raised it. There is also a more human reason this question refuses to go away, and it has nothing to do with seismographs or isotope ratios. It has to do with the strange, persistent human intuition recorded across nearly every culture that has left us a written or oral record that the moon is not simply a rock in the sky. It has been called a god, a boat, a drum, a mirror, a doorway, a watching eye. In the next part of this series, we will look closely at that ancient relationship, at the specific myths, rituals, and astronomical records that early civilizations built around the moon, and at the argument made by a number of researchers in the alternative archaeology and ancient astronaut fields that some of those myths may encode a distant cultural memory of something in the sky that was not simply admired from a distance, but observed up close by beings who left an impression on the earliest storytellers whose words survive into the present. Whether that argument holds up to scrutiny is something we will examine honestly, alongside the more conventional explanation that early humans simply personified the most dominant, mysterious, and cyclically reliable object in their night sky, the way they personified the sun, the rivers, and the storms. For now, as this first part draws to a close, sit with the plain, undecorated facts we've already covered, because none of them require any leap of faith to accept. The moon is disproportionately large for its parent planet. Unlike every other moon in the inner solar system, its size and distance combine to produce a solar eclipse geometry that appears nowhere else we have observed. Its formation, despite 5 decades of dedicated study and an entire haul of rock samples brought back by human hands, remains only partially explained by the leading scientific model. And when astronauts deliberately impacted it in 1969 and in the missions that followed, it did not behave the way a solid, ordinary rock should. It rang. Those are not conspiracy talking points. They are documented, published, and in most cases, uncontested facts. What we do with those facts, what conclusions we are willing to draw from them, and how far we are willing to follow the evidence into stranger territory, is the question this entire series is built to explore. Ancient skies. Long before anyone measured the moon's orbit or split its light through a prism, human beings had already decided it mattered more than almost anything else in the sky. Every civilization that left behind writing, carvings, or oral tradition passed down to us left behind something about the moon too. And the sheer consistency of that pattern across cultures that never had any contact with one another, separated by oceans and millennia, is itself worth pausing on before we even look at the specific stories. In Mesopotamia, in Egypt, in Greece, in China, across Mesoamerica, throughout the Norse world, and among indigenous peoples on nearly every continent, the moon was rarely treated as a passive backdrop. It was a god, a boat, a rabbit, a drum, a severed eye, a woman fleeing across the sky. And in an unusually large number of these traditions, the moon was not simply admired. It was described as having arrived, as having been placed, or as having changed the world the moment it appeared. Starred in Mesopotamia, home to some of the oldest continuous astronomical record-keeping in human history, the Sumerians and later the Babylonians worshipped the moon as the god Nana, known to the Akkadians as Sin, a deity considered senior to the sun god Shamash in the earliest layers of the pantheon, which is itself an interesting reversal of what you might expect from a culture whose agricultural life depended so heavily on the solar calendar. Babylonian astronomers kept meticulous records of lunar cycles for well over 1,000 years, tracking eclipses with enough precision that by the time of the Seleucid era, their priest astronomers could predict eclipses mathematically using cycles like the Saros, an 18-year pattern in the recurrence of eclipses that modern astronomers still use as a teaching tool today. This was not casual sky watching, it was sustained, generational, mathematically rigorous observation conducted by a professional class of scribes and priests whose entire social function revolved around understanding the moon's behavior well enough to predict it. Why a Bronze Age civilization devoted that level of institutional resource to one specific object in the sky, more than to the stars, more consistently than to the planets, is a question mainstream historians answer in terms of omens and agricultural timing. It is also a question ancient astronaut researchers have asked from a very different angle, wondering whether that intensity of attention reflects something closer to surveillance of a returning visitor than casual reverence for a calendar object. Move to Egypt, and the moon splits into several deities depending on the era and region, most prominently Thoth, the ibis-headed god of writing, knowledge, and measurement, and Khonsu, whose name is believed to derive from a root meaning traveler, a reference to the moon's nightly journey across the sky. Thoth's association with the moon is worth sitting with for a moment because Egyptian tradition did not connect the moon to fertility or agriculture the way many other cultures did. It connected the moon specifically to knowledge, to writing, to the keeping of records, and to the measurement of time itself. Egyptian civil calendars and religious calendars both leaned heavily on lunar observation, and Thoth was credited in various strands of Egyptian myth with having invented not just the calendar, but written language itself. A civilization that built pyramids aligned with millimeter precision to cardinal directions and to specific stars was not a civilization prone to careless mythology. When they attached their god of precise measurement and recorded knowledge specifically to the moon, that association reflects, at minimum, a culture that saw something in the moon worth associating with exactness rather than mystery. Greek mythology gives the moon its own goddess, Selene, sister to the sun god Helios, often depicted driving a silver chariot across the night sky, and later increasingly merged in popular religious practice with Artemis, goddess of the hunt and the wilderness. But it is not the goddess herself that has drawn the most attention from researchers looking for anomalies in ancient lunar tradition. It is a strange, persistent claim recorded by multiple classical writers, including Aristotle, Apollonius Rhodius, Hippolytus of Rome, and later the Roman writer Censorinus, that the people of Arcadia, a rugged, isolated region of the Greek Peloponnese, were considered by other Greeks to be proselytes, a word that translates roughly to before the moon. The claim, as recorded across these several independent classical sources, was that the Arcadians were of such ancient stock that their ancestors had lived on Earth before the moon existed in the sky at all. This is an extraordinary thing to find recorded, repeatedly, by serious classical authors who were not writing fiction, but attempting historical and ethnographic description. Mainstream classicists generally treat the proselyte tradition as a boast about antiquity and cultural seniority, a way for Arcadians to claim they were older than everyone else, expressed through poetic exaggeration rather than literal astronomical memory. ancient astronaut researchers read the same tradition very differently, asking why, if this was simply a boast, the specific claim settled on the moon rather than the sun, the stars, or any other feature of the sky, and why the tradition persisted across multiple independent writers over centuries rather than fading as an obvious rhetorical flourish would. The proselyte tradition does not stand alone. Democritus, the 5th century BCE philosopher best remembered today for proposing that matter was composed of indivisible atoms, is reported by later ancient sources to have written about a time before the moon appeared in the sky, treating it as a serious cosmological claim rather than poetry. Anaxagoras, a contemporary of Democritus, taught that the moon was a solid body, not a source of its own light, but a reflector of sunlight, a genuinely advanced insight for the period, and one that got him charged with impiety in Athens for daring to describe a god as an ordinary rock. What is striking is not any single one of these claims in isolation. It is the pattern across independent Greek philosophical traditions, all circling the same unusual idea that the moon was not always there, that its appearance marked a distinct before and after moment in the memory of the earliest people, remembered clearly enough that multiple serious thinkers writing centuries apart felt obligated to address it rather than dismiss it outright. That same before and after structure surfaces well outside the Mediterranean world too, in places with no plausible route of cultural contact with Greece. Among several indigenous peoples of the Americas, oral traditions describe a period before the moon existed, followed by its sudden appearance, often tied to a transformative or catastrophic event. Certain Southern African oral traditions, passed down among some Bushmen and Zulu communities and recorded by early ethnographers, describe the moon as a fragment thrown into the sky, or a being transformed and placed there, again marking its appearance as an event within remembered time, rather than a permanent, unquestioned feature of the world. Chinese tradition holds the story of Chang'e, a woman who drank an elixir of immortality and ascended to the moon, where she is said to remain to this day, a myth so deeply embedded in Chinese culture that it lent its name to the country's actual lunar exploration program in the 21st century. Norse mythology offers its own variation on the theme, with the moon personified as Mani, a young man who drives the moon across the sky in a chariot, perpetually pursued by a wolf named Hati, who is fated, according to the poetic Edda, to finally catch and devour him at Ragnarok, the mythological end of the world. That detail is worth noting because it frames the moon's disappearance not as a routine monthly event, but as an apocalyptic marker, the loss of the moon serving as one of the specific signs that the world itself is ending. Aboriginal Australian traditions, among the oldest continuously practiced oral traditions on Earth, include moon stories that vary enormously between language groups, but frequently share the theme of the moon as a man who was transformed, punished, or exiled into the sky after some transgression, condemned to wax and wane forever as a visible consequence of that original event. Maori tradition tells of Rona, a woman who cursed the moon and was pulled into the sky as punishment, said to remain visible on its surface to this day, a lunar pareidolia myth that appears, in slightly different form, in cultures as far removed from New Zealand as parts of Europe and North America, where people have long seen a face, a rabbit, or a woman with a bundle of sticks in the moon's pattern of Maria and Highlands. The theme of the moon as a place of exile, transformation, or punishment recurs often enough across unrelated traditions that some comparative mythologists treat it as a near-universal archetype, on par with flood myths or trickster figures. But one thread within that broader pattern deserves particular attention here, because it connects more directly than any other ancient tradition to the specific idea at the center of this series: the moon, or the sky more broadly, as a place from which humanity is watched. The apocryphal Book of Enoch, a Jewish religious text dated to roughly the 3rd century BCE and excluded from most modern biblical canons, but preserved in full within Ethiopian Orthodox scripture, describes a group of celestial beings called the Watchers, sent, in the text's own account, to observe humanity from the heavens, who ultimately descend, intervene directly in human affairs, and father a hybrid race called the Nephilim. The text is explicit that the Watchers' original function was observation, a term the book uses directly before their narrative shifts to direct intervention. Ancient astronaut researchers have leaned heavily on the Book of Enoch for decades, arguing that its description of sky-based observers who eventually make direct contact with humanity reads less like pure religious allegory and more like a garbled cultural memory of exactly the kind of scenario this series is built around: an intelligence positioned somewhere above Earth, tasked specifically with watching before anything else happens. The Americas contribute their own layer to this picture, independent of anything happening in Eurasia. The Aztec goddess Metztli and the Inca goddess Mama Killa were both worshipped as senior figures within their respective pantheons, with the Inca in particular maintaining an official state calendar built around lunar observation that Spanish chroniclers, arriving in the 16th century, described as remarkably precise even by their own contemporary European standards. Slavic tradition personified the moon as Maesiats, frequently paired in folk astronomy with the sun as a married or sibling figure. Their relationship used to explain the changing length of days and nights across the seasons. What stands out across this final tour of traditions, spanning from the Andes to Siberia, is not any single culture's story, but the sheer redundancy of the underlying pattern. Independent civilizations, with no meaningful contact between them, consistently elevated the moon into a position of institutional, religious, and calendrical importance disproportionate to what a simple, unchanging rock in the sky would seem to warrant. It is worth returning, one more time, to the strongest version of the mainstream explanation before we move on, because it deserves more than a passing mention. Comparative mythologists, building on more than a century of fieldwork since the discipline's early 20th century founders, argue that human storytelling follows recognizable structural patterns regardless of culture, because human brains, wired the same way, regardless of geography, tend to process dramatic, cyclical, life-relevant phenomena through narrative in broadly similar ways. This is the same reasoning that explains why flood myths appear on nearly every continent without requiring a single global deluge, why trickster figures appear in West African, Norse, and Native American traditions without requiring cultural contact, and why creation myths so often begin with darkness giving way to light. Applied to the moon, this framework predicts almost everything we have just walked through. A bright, cyclical, life-relevant object would naturally accumulate origin stories, transformation myths, and observational rituals across any sufficiently curious species, with no need for actual contact or actual celestial visitors to explain the pattern. This is a genuinely strong argument, grounded in real cross-cultural data, and it likely accounts for the majority of what we have covered in this part. What it accounts for, less comfortably, and what keeps this question from being fully closed, is the specific texture of certain traditions rather than their general existence. A general tendency toward moon myths explains why cultures have moon gods. It explains less neatly why the Watchers of the Book of Enoch are explicitly described as observers before anything else, positioned in the sky specifically to watch, in a text whose broader themes involve none of the fertility or agricultural symbolism that dominates most solar and lunar mythology elsewhere. It explains less neatly why multiple independent Greek philosophers treated the moon's absence from an earlier age as a serious cosmological claim rather than obvious poetic exaggeration, and it explains less neatly why so many building projects, from Stonehenge's Aubrey Holes to the alignments at Chaco Canyon, invested such extraordinary multi-generational effort into tracking the moon's most subtle and least practically useful cycles, patterns like the 18.6-year lunar standstill that offer little agricultural or tidal benefit over simpler monthly observation, and would only matter to a civilization that, for reasons of its own, needed or wanted a truly precise, long-term model of exactly how the moon moved. That explanation is reasonable, well-evidenced, and almost certainly accounts for the majority of lunar mythology across human history. It is worth stating that clearly rather than glossing past it, because a fair examination of the ancient astronaut interpretation has to acknowledge that the conventional anthropological account is not weak or hand-wavy. It is the product of more than a century of careful comparative mythology and ethnographic fieldwork. But the conventional account also does not fully close the door on the more unusual reading, and the reason it doesn't comes down to specificity. A general cultural tendency to build myths around a cyclical object explains why cultures would have moon myths at all. It explains phase cycles, tidal associations, and fertility symbolism reasonably well. It explains less comfortably why several entirely independent traditions, without any plausible contact between them, converged on the specific and unusual claim that the moon had not always been present, as opposed to simply always having been there but growing more or less powerful, more or less favorable, across its cycle, which would be the more expected mythological framing for something people watched change shape every month of their lives. The sudden arrival motif is a narrower, odder claim than a general fertility or tidal association, and its recurrence, however it is ultimately explained, is one of the more genuinely curious data points in comparative mythology. Beyond myth, ancient cultures left behind physical structures that reveal just how seriously they took lunar observation, structures whose precision goes well beyond what casual sky watching would require. Stonehenge, built and rebuilt over centuries beginning around 3000 BCE, is most commonly discussed in terms of its solar alignments, particularly the famous alignment with the summer solstice sunrise. Less widely known outside archaeoastronomy circles is the substantial body of research suggesting that the monument's Aubrey holes, a ring of 56 pits surrounding the main stone circle, may have functioned as a device for tracking and predicting lunar eclipses, using a counting system tied to lunar cycles across multiple years. If that interpretation holds, and it remains debated among archaeologists, it would mean a Neolithic society with no writing system, no metal tools in its earliest construction phases, and no wheeled transport for its largest stones, nonetheless built a structure capable of tracking a cycle that takes decades to fully repeat. The Nebra sky disk, a bronze artifact unearthed in Germany and dated to roughly 1600 BCE, depicts what most archaeologists interpret as a crescent moon, a full moon or sun, and a cluster of stars widely believed to represent the Pleiades, arranged in a way that some researchers argue encodes a system for reconciling the lunar and solar calendars, a genuinely sophisticated astronomical problem that Bronze Age Europe is not typically credited with having solved. In Mesoamerica, Maya astronomers achieved a level of lunar calendrical precision that remains startling even by modern standards, calculating the length of the lunar month to within a few hundredths of a day of the modern measured value, embedding those calculations into inscriptions at sites like the Temple of the Cross at Palenque, centuries before the invention of the telescope. None of these structures or artifacts, on their own, proves anything beyond what mainstream archaeology already credits ancient societies with: sustained, careful, multi-generational naked-eye astronomy conducted by dedicated observer classes who had every practical reason, religious, agricultural, and calendrical, to become extraordinarily good at tracking the moon. But taken together with the mythological pattern we just walked through, they paint a picture of a species that treated the moon, consistently and across cultures with no contact with one another, as an object worth watching more closely, more carefully, and with more institutional investment than almost anything else available to the naked eye. Ancient astronaut researchers argue that this pattern of intensive, precise, cross-cultural attention is exactly what you would expect if early humans really were, at some point in the deep past, observing something in the sky that behaved unusually, something whose motion or appearance rewarded close tracking in a way a purely natural, purely predictable object would not have. Mainstream historians argue, with substantial evidentiary backing, that the pattern is exactly what you would expect from a species dependent on lunar-linked tides and cycles for hunting, planting, and reproduction, developing sophisticated tracking systems purely out of practical necessity, no unusual behavior required. Both explanations can be true at once, and untangling how much of the ancient world's obsession with the moon reflects ordinary human pattern recognition applied to an ordinary object versus something stranger encoded in the deepest layers of human memory is not a question this series can settle definitively in one part, or perhaps in any number of parts. It was the Book of Enoch's Watchers, along with similar sky observer motifs scattered across Sumerian, Egyptian, and Mesoamerican tradition that formed much of the raw material for the modern popularization of ancient astronaut theory in the second half of the 20th century. Swiss author Erich von Däniken's 1968 book, Chariots of the Gods, became an international bestseller by arguing that numerous ancient monuments, texts, and artworks depict contact with extraterrestrial visitors. And while von Däniken's specific claims about individual sites have been extensively challenged and, in a number of well-documented cases, outright debunked by archaeologists over the decades since, his work is credited, even by critics, with popularizing the broader framework this series operates within. The idea that ancient religious and mythological material might preserve distorted, symbolic memories of real, non-human contact, rather than being purely imaginative invention.
A decade later, the American writer Zecharia Sitchin advanced a more specific and more heavily disputed set of claims, built around his own translations of Sumerian cuneiform texts, proposing an entire cosmology involving a planet called Nibiru and a species called the Anunnaki. Sitchin's translations have been rejected almost universally by professional Assyriologists and Sumerologists, who argue that his readings of the cuneiform source material do not hold up against the actual linguistic evidence. It is worth being direct about that scholarly rejection here, because a fair series does not get to borrow the cultural momentum Sitchin's work generated while quietly ignoring how thoroughly his specific textual claims have been contested by the people best qualified to evaluate them. What survives Sitchin's discredited philology, and what remains genuinely interesting independent of it, is the underlying observation that predates him by millennia, that an unusually large number of ancient traditions developed independently across the globe describe the sky, and the moon specifically, as a place associated with watching, arrival, and consequence, rather than simple passive scenery. Physical archaeoastronomy adds one more thread worth including here. At Chaco Canyon in present-day New Mexico, the ancestral Puebloan people built structures, most famously a rock art spiral at a site now called the Sun Dagger, that appear to track not just the solar year, but the far more subtle 18.6-year lunar standstill cycle, a wobble in the moon's orbital extremes that takes nearly 2 decades to complete and is difficult to detect without sustained, multi-generational observation. Several major buildings within Chaco Canyon appear aligned to the northern and southern limits of this standstill cycle, suggesting the people who built them were tracking a lunar pattern so gradual that no single observer could have confirmed it within one lifetime, meaning the knowledge had to be deliberately preserved, taught, and verified across multiple generations purely to keep watching the moon. What the ancient record does establish, beyond reasonable dispute, is that the modern fascination with the moon as something more than a rock is not a 20th century invention born of science fiction and Cold War anxiety. It is the continuation of something that shows up in nearly every culture we have written or oral records for, stretching back as far as those records go. The question of what exactly the moon is and why it commands the attention it does is not new. It may be the oldest question our species has ever asked and never fully answered. There is one more strand of Mesopotamian material worth including before we close this part, because it bridges directly into the observational theme this series keeps returning to. The Enuma Elish, the Babylonian creation epic, describes the god Marduk fixing the celestial bodies in place after his cosmic battle, assigning the moon god Nana specific duties that include marking the days and, notably, standing as a fixed reference point against which the movements of other bodies could be measured and verified. The text describes this in explicitly administrative language, assigning duties and jurisdictions the way a bureaucratic decree would, a strikingly different register from the more romantic or transformative language used in Greek, Norse, or Aboriginal lunar myths. Some researchers who study the ancient astronaut hypothesis point to this administrative framing as significant in itself, arguing that a creation myth describing the moon as an object assigned a fixed monitoring function, phrased in the language of bureaucratic order rather than divine romance, reads differently than the majority of lunar folklore surveyed elsewhere in this part. Mainstream Assyriologists respond that the administrative tone of the Enuma Elish reflects the broader bureaucratic character of Babylonian civilization itself, a society organized around temple administration, legal codes, and centralized record-keeping, and that its creation myth simply reflects the cultural lens of the people who wrote it. the same way agricultural societies produce agricultural myths and seafaring societies produce myths about the ocean. Taken as a whole, the ancient record leaves us with two honest, coexisting conclusions rather than one tidy answer. The first is that nearly everything covered in this part can be explained, adequately and without invoking anything beyond ordinary human psychology, by the moon's unique visibility, its dramatic phase cycle, and humanity's universal tendency to wrap significant natural phenomena in narrative and ritual. The second is that within that broad and well-explained pattern sits a smaller, harder-to-dismiss cluster of specific claims: the Proselenite tradition, the Watchers of Enoch, the administrative language of the Enuma Elish, the extraordinary multi-generational precision of sites like Chaco Canyon and the Aubrey Holes that resist easy absorption into the general theory, and that have provided the raw material for every serious version of the ancient astronaut hypothesis advanced since the mid-20th century. This series is not going to resolve that tension in this part, and it would be dishonest to pretend a tidy resolution exists. What we can do is carry both conclusions forward together, the well-supported general explanation and the smaller set of genuine outliers, as we move from myth into modern measurement. That question took on an entirely new shape in the 20th century, once the tools available to answer it stopped being limited to the naked eye and the careful counting of days. In the next part of this series, we turn to the modern scientific account of the moon's origin, the giant impact hypothesis, and to the genuine, published, peer-reviewed problems that continue to complicate it even among scientists who accept it as the best model currently available. Because before we can properly evaluate the claim that the moon might be artificial, we first have to understand, in detail, exactly how much of its natural origin story science has actually managed to prove, and exactly how much of it remains, even now, an open and unfinished question. A world without an origin story. Science has its own creation myths, and like the myths we spent the last part examining, they were revised, discarded, and replaced more than once before the version most people accept today ever took shape. Before we can fairly evaluate whether the moon might be something other than a natural satellite, we need to understand exactly how confident and how recently confident mainstream planetary science actually is about how it formed at all. That confidence is more recent and more qualified than most popular science coverage lets on. For most of the 20th century, there were three competing scientific explanations for the moon's existence, and all three of them are now considered wrong, or at best, deeply incomplete by the very scientists who once championed them. The first was the fission theory, proposed in 1878 by George Darwin, son of Charles Darwin, who suggested that early Earth spun so rapidly on its axis that a portion of its molten mass tore away under centrifugal force and flew into orbit, eventually cooling into the moon. For decades, this theory came packaged with a specific, almost romantic corollary: that the scar left behind by this violent departure was the Pacific Ocean basin, its shape and size popularly cited as evidence of exactly where the moon had been torn from. The fission theory dominated textbooks well into the mid-20th century. It also turned out to be wrong on nearly every count that could be checked. The Pacific Basin, geologists eventually established, is a comparatively young feature formed by plate tectonics, far too recent and far too shallow to be a 4.5 billion-year-old wound. And the physics itself never worked cleanly. No plausible early rotation rate for Earth generates enough centrifugal force to fling off a moon-sized mass in the way Darwin's model required, a problem that became more apparent, not less, as computational modeling improved through the 20th century. The second classical theory was the capture theory, which proposed that the moon formed elsewhere in the solar system entirely, as an independent body, and was later captured by Earth's gravity as it passed too close. The same basic mechanism believed to explain how Mars acquired its two small moons, Phobos and Deimos. Capture theory had the advantage of not requiring any unusual event in Earth's own history, but it ran into a different, equally serious problem: orbital mechanics. Capturing a large passing body into a stable, nearly circular orbit is extraordinarily difficult without some mechanism to bleed off the enormous excess energy involved, and no proposed mechanism, atmospheric drag, tidal dissipation, or otherwise, adequately explained how a body the size of the moon could have been captured into an orbit as clean and stable as the one we observe, rather than being flung back out into space or crashing directly into Earth. The theory also struggled badly to explain the compositional similarities between lunar and terrestrial rock, similarities that, as we will see, would later become central to an entirely different scientific controversy. The third classical theory, sometimes called co-accretion or the sister theory, proposed that the Moon and Earth formed together, side by side, condensing from the same regional disk of dust and gas that built the early solar system, essentially as twins born from the same material at the same time and place. This theory elegantly avoided the physics problems that plagued both fission and capture, but it created a different one. If Earth and the Moon formed from the same local material at the same time, there is no obvious reason their overall densities and core sizes should differ as dramatically as they do. Earth has a large iron core making up roughly half its radius. The Moon's core, by contrast, is small, estimated today at only around 20% of its radius, and low in iron relative to the rest of its mass. A shared, simultaneous formation from identical local material struggles to explain why one body ended up so iron-rich at its core and the other so iron-poor. By the early 1970s, planetary science had three competing theories for the Moon's origin, and each one was seriously wrong about something fundamental. This is worth sitting with because it means that for most of the space race, for the entire span of the Apollo program's planning and execution, humanity sent astronauts to the Moon without a working scientific explanation for what the Moon actually was or how it had come to exist. The astronauts who walked on its surface in 1969 did so while the scientific community back home was still fundamentally uncertain about the object beneath their boots. What finally broke the impasse was not a new theory, but new evidence, brought back in the astronauts' own sample bags. Apollo missions returned a combined total of roughly 840 pounds of lunar rock and soil to Earth, and the isotopic analysis of those samples, conducted over the following years, delivered a result that ruled out capture theory almost immediately. Oxygen isotope ratios, a kind of chemical fingerprint that varies depending on where in the early solar system a body formed, showed that lunar rock and terrestrial rock were nearly identical, far too similar for the Moon to have formed independently elsewhere in the solar system and later been captured. Whatever had made the Moon, it had used material that came from the same general neighborhood, chemically speaking, as the material that made Earth. That single finding narrowed the field considerably, eliminating capture theory and putting real pressure on fission and co-accretion, neither of which fully accounted for the core size discrepancy we just walked through. The resolution came in 1975 when planetary scientists William Hartmann and Donald Davis, working independently but arriving at complementary conclusions alongside Canadian astronomer Alistair Cameron and his colleague William Ward, proposed what has become known as the giant impact hypothesis. The model suggests that in the chaotic final stages of planet formation, roughly 4.5 billion years ago, a Mars-sized protoplanet, since given the name Theia after the mythological mother of the moon goddess Selene, collided with the young, still-forming Earth in a glancing, off-center impact. The collision was violent enough to partially melt and vaporize both bodies, fleeing a vast ring of superheated debris into orbit around the reforming Earth. Within a remarkably short span of time by geological standards, potentially as little as a few decades to a few centuries according to some simulations, that debris ring coalesced under its own gravity into the Moon. The giant impact hypothesis solved several problems at once, and its explanatory power is exactly why it displaced its three predecessors and became the dominant model within about a decade of its proposal. It explained the core size discrepancy neatly. Theia's own iron core in most simulations sank quickly into Earth's much larger gravitational well during the collision, merging with Earth's core rather than ending up in the debris ring, which is why the material that became the Moon was disproportionately poor in iron compared to Earth as a whole. It explained the general chemical kinship between Earth and lunar rock, since much of the debris ring was assumed to originate from Earth's own outer layers, vaporized and ejected during the impact, alongside material from Theia itself. And it explained the angular momentum of the Earth-Moon system, the specific combination of Earth's rotation speed and the Moon's orbital motion, reasonably well, since a large off-center impact naturally imparts significant spin to the resulting system, unlike the calmer processes proposed by co-accretion. For those reasons, the giant impact hypothesis has been the dominant scientific consensus since roughly the mid-1980s, and it remains so today. It appears in textbooks, museum placards, and popular science coverage as settled fact, presented with a confidence that, in fairness to the scientists who study it directly, does not always reflect how contested certain aspects of the model remain within the specialist literature. And this is the part of the story most popular coverage leaves out entirely. The very isotopic evidence that helped kill capture theory in the 1970s has, since the early 2000s, become one of the giant impact hypothesis's own biggest headaches, in a controversy planetary scientists themselves have taken to calling the lunar isotopic crisis. Here's the problem in plain terms. Computer simulations of the giant impact consistently predict that the moon should be composed primarily of material from Theia, typically somewhere between 60 and 90% Theia material, depending on the specific impact angle and speed modeled, with only a smaller fraction of the debris ring coming from Earth's own vaporized crust and mantle. If that prediction is correct, the moon's chemical fingerprint should differ measurably from Earth's, reflecting Theia's presumably distinct composition, formed as it was in a different part of the early solar system. But when scientists measure the actual isotopic ratios in Apollo lunar samples, for oxygen, for titanium, for chromium, and for several other elements used as formation fingerprints, the moon's composition matches Earth's own mantle to a precision that has startled researchers in paper after paper since the early 2000s.
In some of these isotopic systems, the match between Earth and Moon is closer than the match between Earth and any known meteorite class, meaning the Moon looks, chemically, more like a piece of Earth than like debris from an entirely separate protoplanet ever should, given how differently formed bodies in the early solar system are expected to vary from one another. This is not a fringe objection. It has been published, debated, and refined in mainstream journals, including Nature, Science, and the Journal of Geophysical Research, by planetary scientists who broadly accept the giant impact framework and are working to fix it, not to overturn it. Several proposed patches have emerged. One line of research, advanced by scientists, including Kaveh Pahlavan and David Stevenson, suggests that in the aftermath of the impact, the vaporized debris ring and Earth's own atmosphere existed as a connected, high-temperature, high-pressure structure for long enough that the two thoroughly mixed and chemically equilibrated before the moon fully condensed, essentially averaging out any compositional differences between Theia's material and Earth's material before the moon finished forming. A related and increasingly influential model, developed by Simon Locke and Sarah Stewart and published in 2017, proposes that the impact was energetic enough to briefly transform Earth and the impacting debris into an entirely new kind of structure, a donut-shaped cloud of vaporized rock they named a synestia, within which Earth and the future moon's material were, for a period, not even clearly separate bodies at all, allowing far more thorough mixing than earlier, gentler impact models assumed. Other researchers have proposed that the moon formed not from one giant impact, but from a series of smaller impacts over an extended period, each contributing debris that mixed more gradually with Earth's own material across a longer span of time, which could also help explain the closer than expected chemical match. Each of these patches is a legitimate, actively researched line of inquiry, not evidence of a hypothesis in collapse, but it is important to be precise about what they represent. Modifications required because the original, simplest version of the giant impact model, the one still presented to the public as settled science, does not actually match the isotopic data well enough on its own. No single patched version has yet achieved the kind of broad, unanimous acceptance among specialists that the giant impact framework itself achieved in the 1980s. The debate over exactly how the impact happened, how much mixing occurred, and how long it took remains genuinely open in the specialist literature, even as the broader claim that some kind of giant impact occurred remains solidly supported. A second unresolved puzzle involves the moon's volatile elements, chemical compounds, and metals with relatively low boiling points like potassium, sodium, and water that would have been driven off by the extreme heat of a giant impact more easily than heavier, more heat-resistant elements. The giant impact hypothesis correctly predicts that the moon should be depleted in these volatiles compared to Earth, and it is. But subsequent analysis of lunar samples, including volcanic glass beads returned by Apollo missions and later re-examined with more sensitive instruments in the 2000s and 2010s, revealed trace amounts of water locked inside lunar minerals at concentrations higher than the simplest impact models predicted, suggesting the moon retained more of its original volatile content, or reacquired volatiles from some other source, than a total, catastrophic vaporization event should have allowed. Scientists continue to debate whether this water arrived through later cometary and asteroid bombardment, whether it survived the formation process in isolated pockets that never fully vaporized, or whether it reflects a formation process gentler, in certain respects, than the standard model assumes. There is a third puzzle worth naming here, one that connects directly to a subject we will return to in far greater depth in the next part of this series: the question of what is actually happening inside the moon today, and whether it ever once had a magnetic field like Earth's. The moon has no global magnetic field now, but paleomagnetic analysis of Apollo rock samples reveals that many of them are magnetized, meaning they cooled and solidified in the presence of a magnetic field billions of years ago, a field that must have been generated by some kind of dynamo process inside a young, molten lunar core. The strength of that ancient field, based on the magnetization data, appears to have been surprisingly powerful for a body as small as the moon. And the field appears, from the range of rock ages studied, to have persisted for far longer than most theoretical models of a small lunar core can easily sustain, explaining how an object with a core as small as the moon's generated a magnetic field that strong for that long without a larger body's gravitational and thermal resources to sustain it, remains an active area of research and genuine disagreement. One more item on the growing list of specifics that the giant impact hypothesis, in its current form, has not fully closed the book on. The giant impact hypothesis did not become the dominant model overnight, and the story of how it displaced its competitors is worth telling in a little more detail, because it illustrates just how contested lunar origin science was within living memory. Hartman and Davis published their version of the hypothesis in the journal Icarus in 1975. The same year, Cameron and Ward independently presented a similar concept at a lunar and planetary science conference. For nearly a decade afterward, the idea competed on relatively even footing with revised versions of fission, capture, and co-accretion theory, none of which their proponents were willing to abandon without a fight. The turning point came at a dedicated scientific conference held in Kona, Hawaii in 1984, titled simply The Origin of the Moon, where researchers from competing camps presented their models side by side and subjected each other's work to direct scrutiny. It was at that conference, and in the flurry of papers that followed it through the rest of the 1980s, that the giant impact hypothesis emerged as the clear frontrunner, not because it was proven beyond doubt, but because it explained more of the accumulated Apollo data with fewer ad hoc assumptions than its rivals could manage. That is a genuinely normal and healthy way for a scientific consensus to form. It is also worth remembering that the consensus is not, and has never claimed to be, a finished, unanimous, fully solved picture. It is the current leading model, arrived at through comparison with weaker alternatives, still being actively revised in its details 4 decades later. The angular momentum problem we touched on earlier deserves a slightly closer look, because later research complicated the tidy version of the story. The original Hartman-Davis and Cameron-Ward models, run through modern simulation software, tend to slightly underproduce the angular momentum actually observed in the Earth-Moon system today, meaning a simple, moderate speed, moderate angle glancing impact does not quite impart enough spin to match reality. This has pushed researchers toward what are called high angular momentum impact models, involving either a faster spinning early Earth than previously assumed, a more direct and energetic collision angle, or, in some versions, 2 smaller sequential impacts rather than one large one. Each adjustment brings its own trade-offs, and finding a single impact scenario that simultaneously satisfies the observed angular momentum, the observed core size, and the observed isotopic near identity between Earth and Moon has proven to be a persistently difficult needle to thread, which is precisely why models like Locke and Stewart's Synestia framework, published in the Journal of Geophysical Research in 2017, have gained traction. Their model proposes an impact energetic enough to briefly merge Earth and the ejected debris into a single, rapidly rotating, donut-shaped mass of vaporized and partially vaporized rock, hot enough that no firm boundary existed between Earth and future Moon material for a period, allowing the kind of thorough compositional mixing needed to explain the isotopic data, while still permitting enough angular momentum and eventual mass separation to produce the system we see today. It is currently one of the more actively cited refinements in the field, though far from the only one under serious consideration. It also helps to place the Moon's iron deficit in a wider comparative context, because the contrast with our other rocky planetary neighbors sharpens exactly how unusual the Moon's internal structure is. Mercury sits at the opposite extreme, an unusually iron-rich planet whose core makes up roughly 85% of its radius, so metal-heavy relative to its size that planetary scientists have proposed Mercury may have lost much of its rocky outer mantle to an ancient impact of its own, stripping away lighter material and leaving the dense core disproportionately exposed. Earth sits in the middle, with a core radius around 55% of the total. The Moon sits at the other extreme from Mercury, with a core estimated at only around 20% of its radius, by far the smallest proportional core of any of the terrestrial bodies. Seen across that comparative range, the Moon is not simply a smaller version of Earth. It is the most metal-poor, rocky body of its size class that we have detailed data for anywhere in the inner solar system. An outlier requiring a genuinely unusual formation history to explain. However, that history is ultimately modeled. The water content puzzle also has a more specific history worth including, because the story of its discovery says something about how much the standard model has already had to bend since the Apollo era ended. When the Apollo astronauts collected volcanic glass beads from the lunar surface in the early 1970s, decades of analysis using the instruments then available found them to be essentially bone dry, a result fully consistent with the standard, violent, moisture-boiling giant impact story. That consensus held for over 30 years, until a team led by geochemist Alberto Sal re-examined the same Apollo 15 and Apollo 17 glass beads in 2008 using a newer generation of ion microprobe technology, sensitive enough to detect water concentrations the older instruments simply could not measure. The beads were not dry after all. They contained measurable water, trapped inside volcanic glass formed from magma that originated deep within the lunar interior, suggesting the Moon's interior retained meaningfully more water than the original post-impact models allowed for. Follow-up studies through the 2010s pushed the estimated water content of the lunar mantle even higher in certain regions, based on mineral inclusions called melt inclusions that appear to have been sealed off from the vacuum of space before their water could escape, preserving a more direct sample of the deep lunar interior's original composition. This is a genuine example of new instrumentation overturning a decades-old scientific certainty, not through error, but because the tools available in the 1970s were simply not sensitive enough to see what was actually there. And it is a useful reminder for how much of what still passes for settled lunar science may yet be revised again as instrumentation continues to improve. One further anomaly rounds out this part, and it comes not from Apollo-era data, but from a considerably more recent mission. In 2014, NASA's Grail mission, which mapped the Moon's gravitational field with extraordinary precision using a pair of orbiting satellites that tracked minute changes in the distance between them as they passed over regions of differing lunar density, revealed a massive, previously unknown rift structure buried beneath the Procellarum region on the Moon's near side, an area already notable for hosting one of the largest expanses of dark volcanic maria on the entire lunar surface. The structure, roughly rectangular and enormous in scale, does not match the circular pattern expected from a simple ancient impact basin, and its origin remains a genuinely open question within lunar geophysics, with proposed explanations ranging from ancient volcanic rifting driven by internal cooling and contraction to the lingering thermal aftermath of whatever process originally formed the near-side-far-side asymmetry we will examine in detail several parts from now. It is one more entry in a growing list of features that modern, high-precision instruments continue to uncover beneath a surface the Apollo program only ever sampled in a handful of scattered locations. A reminder that even after more than half a century of study, the interior structure of the Moon is still being actively mapped, not simply confirmed. Taken together, the isotopic crisis, the angular momentum mismatch, the unexpectedly wet interior, and structures like the Procellarum Rift do not describe a scientific field in crisis, and they should not be read as evidence that planetary scientists secretly doubt the moon formed through natural processes. They describe a field doing exactly what a healthy field does, continuing to test its best available model against new data, and continuing to find details that model has not yet fully absorbed. That distinction between an active, ongoing scientific refinement and a field on the verge of collapse matters enormously for how you should weigh everything that follows in this series. Genuine, published scientific uncertainty, like the isotopic crisis or the angular momentum mismatch, is frequently picked up by less careful sources and stretched well past what the original researchers actually argue. A planetary scientist publishing a paper on isotopic equilibration in the aftermath of a giant impact is not expressing doubt that the moon formed through natural processes. They are refining the mechanics of a process they are confident happened. When that kind of careful, technical uncertainty gets flattened into a headline suggesting scientists don't know how the moon formed, or worse, into a claim that scientists secretly suspect an artificial origin, something real gets lost, and something misleading gets manufactured in its place. This series is going to keep returning to genuine anomalies throughout the parts that follow, and it owes you the same honesty in each case. An open question in the technical literature is not the same thing as an admission of an alien moon, even when the two get described in identical language by less careful sources. It is important to say that clearly, because it would be intellectually dishonest to present an active scientific debate about impact mixing ratios as though it were secretly a debate about extraterrestrial engineering. The giant impact hypothesis remains, by a wide margin, the best supported and most thoroughly evidenced explanation for the moon's origin that science currently has, and the ongoing refinements to it, the synestia model, the equilibration models, the multiple impact models, represent exactly the kind of normal, healthy scientific process by which a strong theory gets stress tested and improved as new data comes in. What this part is meant to establish, honestly and without exaggeration, is something narrower and more defensible, that the moon's origin is not a closed case. It is an active, contested, unfinished area of planetary science, populated by real anomalies that professional researchers openly acknowledge, argue about, and have not yet fully resolved, more than 50 years after the Apollo program supposedly gave us all the answers we needed. That unfinished quality matters for the rest of this series, because it means the door genuine scientific uncertainty leaves open is not a door conspiracy theorists forced ajar out of nothing. It is a door mainstream planetary science has left open itself in its own journals, using its own data. What walks through that door in the parts that follow is a different question entirely, and it starts with what happened when the astronauts who collected those very rock samples deliberately crashed their spacecraft into the surface they had just left, and the moon responded in a way nobody in that era's mission control was fully prepared for. The race to reach it. No nation spends the equivalent of $250 billion in modern currency, employs 400,000 people at its peak, and risks human lives on top of an untested rocket the height of a 36-story building purely out of scientific curiosity. To understand what the Apollo program actually was and why it moved as fast and as recklessly as it did, you have to set the science aside for a moment and look at the geopolitics that put it in motion, because the geopolitics explains the timeline in a way the science alone never could. On October 4, 1957, the Soviet Union launched Sputnik 1, a beach ball-sized satellite that did nothing but orbit the Earth and emit a steady radio beep, and the effect on the United States was immediate and disproportionate to the object's actual capabilities. Sputnik proved the Soviets had rockets powerful enough to put an object into orbit, and a rocket powerful enough to do that was, with only modest modification, powerful enough to deliver a nuclear warhead to any city on Earth. The panic that followed, often remembered today as the Sputnik crisis, reshaped American science education, funding priorities, and defense policy almost overnight, and led directly to the creation of NASA in 1958 as a civilian space agency explicitly intended to compete with and be seen to compete with Soviet achievements in space. The Soviets kept adding to the pressure. In April 1961, cosmonaut Yuri Gagarin became the first human to orbit the Earth. Another clear Soviet first, delivered before the United States had even managed to put an astronaut into a full orbital flight of its own. It was against that backdrop, weeks after Gagarin's flight and following the embarrassing failure of the CIA-backed Bay of Pigs invasion of Cuba, that President John F. Kennedy stood before a joint session of Congress on May 25, 1961, and committed the United States to landing a man on the moon and returning him safely to Earth before the end of the decade. It is worth being clear-eyed about what that commitment actually was. It was not primarily a scientific proposal. Kennedy's own advisors and Kennedy himself in private conversations that later became part of the historical record were explicit that the goal was chosen because it was dramatic, because it was achievable within a fixed and politically useful time frame, and because it played to emerging American strengths in large-scale heavy-lift rocketry, rather than to areas like early orbital rendezvous techniques, where the Soviets already had a head start. The moon landing was, first and foremost, a demonstration of national capability aimed at a Cold War audience, a way of proving that the American system of government and industry could outbuild and out-organize the Soviet system on the largest possible stage. That it also produced genuine, enduring scientific value is true and important, and something this series will spend real time on. But the scientific value was in the political calculus that actually funded and scheduled the program, a secondary justification layered onto a primarily military and geopolitical undertaking. The scale of what followed is difficult to overstate even now. At its peak, the Apollo program employed roughly 400,000 people across NASA and its contractor network, spread across facilities in nearly every state in the country. Its total cost through the end of the program is generally estimated at around $25 billion in the currency of the era, a figure that translates to somewhere in the neighborhood of $250 billion in today's money, consuming, at its height in the mid-1960s, more than 4% of the entire federal budget, a share of national spending that no peacetime scientific or exploratory program has approached before or since. The Saturn V rocket developed to carry astronauts to the moon remains, to this day, the most powerful rocket ever successfully flown, standing 363 feet tall, generating over 7.5 million pounds of thrust at liftoff and consuming roughly 15 tons of fuel every single second of its ascent. That scale came with real cost in human life, and the program's early history includes a tragedy that is sometimes underplayed in retrospectives focused on the eventual triumph of the landing itself. On January 27, 1967, during a routine ground test of the Apollo 1 command module, a flash fire swept through the cabin's pure oxygen atmosphere, killing astronauts Gus Grissom, Ed White, and Roger Chaffee in under 30 seconds, unable to open the module's inward opening hatch quickly enough to escape. The disaster halted crewed Apollo flights for 20 months, while NASA redesigned the spacecraft's hatch, wiring, and cabin atmosphere, changes that very likely prevented a similar disaster from occurring during an actual mission, and that stand as a grim reminder of how experimental and unforgiving the entire undertaking really was, executed on a political timeline that left little margin for the kind of caution a purely scientific program, unconstrained by a Cold War deadline, might have chosen to take. The program's momentum resumed with Apollo 7 in October 1968, the first crewed test of the redesigned command module in Earth orbit, followed 2 months later by one of the boldest single decisions of the entire program. Apollo 8, launched in December 1968, was originally planned as another Earth orbit test. But NASA, spurred by intelligence suggesting the Soviets might be preparing their own crewed lunar flyby, made the decision to send the mission all the way to the moon instead, on only the second crewed flight of the redesigned spacecraft and the first time human beings had ever left low Earth orbit. Astronauts Frank Borman, Jim Lovell, and William Anders orbited the moon 10 times on Christmas Eve of 1968, reading passages from the Book of Genesis in a broadcast watched by thousands of millions of people worldwide, and captured, almost by accident, one of the most consequential photographs in the history of the space program. Earthrise, an image of the whole Earth rising over the barren lunar horizon, a picture credited by historians and environmentalists alike with reshaping how an entire generation understood the fragility and unity of their home planet, seen for the first time from far enough away to fit inside a single frame. 7 months later, on July 20th, 1969, Apollo 11 achieved Kennedy's goal with less than 5 months of the decade to spare. Neil Armstrong and Buzz Aldrin landed the lunar module Eagle in the Sea of Tranquility, while Michael Collins orbited overhead alone in the command module, and the landing itself came far closer to disaster than most popular retellings acknowledge. As Armstrong took manual control during the final approach, he found the automated guidance system steering the module toward a boulder-strewn crater unsuitable for landing, forcing him to fly the spacecraft manually over the hazard while fuel reserves dropped toward levels mission planners had identified as the abort threshold, landing with what NASA's own post-mission analysis estimated at somewhere between 20 and 25 seconds of usable fuel remaining. It was, by the standards of an agency that prided itself on exhaustive planning, an improvised save executed under pressure with margins far thinner than the calm television commentary of the day let on. 5 more crewed landings followed between 1969 and 1972, each expanding the scope of what was collected and measured on the surface. Apollo 12, in November 1969, landed with enough precision to walk to a previously soft-landed robotic probe, Surveyor 3, and brought pieces of it home for analysis, while its spent lunar module ascent stage deliberately crashed back into the surface after the astronauts departed, produced the seismic result that will occupy the entirety of the next part of this series. Apollo 13 in April 1970 became the program's most famous near catastrophe when an oxygen tank ruptured en route to the moon, forcing the crew to abandon their planned landing entirely and use the lunar module as a makeshift lifeboat to survive the return journey, a crisis resolved through improvisation that is still taught in engineering and crisis management courses today. That crisis deserves a fuller account than a single sentence, both for its drama and for what it reveals about the thin margins the entire program operated within. On April 13, 1970, roughly 200,000 miles from Earth, the tank ruptured following a damaged wire installed months earlier during routine ground testing, an ordinary manufacturing defect that nearly killed 3 astronauts in deep space. Commander Jim Lovell, along with Jack Swigert and Fred Hayes, powered down the crippled command module almost entirely and retreated into the lunar module, a craft designed to sustain 2 astronauts on the surface for a day and a half, and stretched its resources to keep 3 astronauts alive for 4 days during the long coast back to Earth, relying on an improvised carbon dioxide scrubber assembled from spare parts and duct tape by engineers on the ground, a solution still taught today as a case study in crisis problem solving under extreme constraint. Apollo 14 returned to the type of highland terrain Apollo 13 had been aiming for. Apollo 15, 16, and 17, flown between 1971 and 1972, each carried a battery-powered lunar rover, extending the astronauts' range across the surface from a few hundred yards on foot to several miles, and each carried increasingly sophisticated scientific instrument packages, deployed and left running on the surface long after the astronauts themselves departed. That instrument package, known as the Apollo Lunar Surface Experiments Package, or ALSEP, is the detail this part exists to set up, because it is the single thread that connects the Apollo program's engineering triumph to the anomaly at the center of the next several parts of this series. Beginning with Apollo 12 and continuing through Apollo 16, astronauts deployed seismometers, heat flow probes, magnetometers, and other instruments on the lunar surface, wired to small nuclear-powered generators that kept them transmitting data back to Earth for years after the astronauts who installed them had gone home. These were not one-time readings taken during a brief surface stay. They were a functioning, unmanned scientific network quietly recording the moon's internal behavior around the clock that remained operational until NASA made the decision to shut the network down in September 1977 purely for budgetary reasons, having already accomplished far more than its original mission planners had dared to hope for. None of that hardware or crew readiness happened by accident, and the training regimen NASA built to prepare astronauts for lunar geology work is itself an underappreciated part of the story. Early in the program, NASA recognized that test pilots, however skilled at flying, had no particular training in recognizing geologically significant rock formations, and the agency built an extensive field geology curriculum in response, sending astronauts to Meteor Crater in Arizona to study impact geology firsthand, to Hawaii's volcanic fields to study basalt formations comparable to the lunar Maria, and to Iceland's volcanic terrain for similar reasons, all under the instruction of professional geologists brought in specifically to turn pilots into competent field scientists capable of making real-time sampling decisions on the lunar surface, hundreds of thousands of miles beyond any expert's ability to guide them in the moment. That investment paid off directly in discoveries like the Genesis rock and the orange volcanic glass, both identified in real time by astronauts trained well enough to recognize their significance without a geologist standing beside them, aside from Schmidt himself on the final mission. The cancellation of the program, when it came, was documented in budget terms with unusual specificity, and it is worth walking through those specifics because they support the mainstream explanation more solidly than popular retellings often bother to establish. NASA's overall budget peaked in fiscal year 1966 at just under $6 billion, representing that 4% plus share of total federal spending mentioned earlier, and it had already begun a steady decline before Apollo 11 ever landed, driven by the mounting costs of the Vietnam War and President Johnson's Great Society domestic programs competing for the same finite pool of federal funding. By the time Richard Nixon's administration reviewed the program's future in 1969 and 1970, the White House's own Office of Management and Budget was pushing for deeper cuts than NASA itself wanted, and it was in that budgetary environment that Apollo 18, 19, and 20 were formally canceled, with 18 and 19's already built Saturn V hardware eventually repurposed, one to launch the Skylab space station and others relegated to museum display, having never flown at all. Nixon's own stated preference, reflected in his 1972 announcement approving the Space Shuttle program, was for a reusable, lower-cost vehicle focused on establishing routine access to low Earth orbit, rather than continued expensive deep space missions, a strategic pivot away from exploration and toward what the administration characterized as more sustainable, economically justifiable space infrastructure. That pivot, whatever its merits, is the documented, on-the-record reason the program ended when it did, laid out in budget memos and public statements available in the historical record, not a secret rationale requiring speculation to uncover. The ALSEP network deserves a slightly fuller description here, since the next several parts of this series depend on understanding exactly what it was. 5 of the 6 landing missions, Apollo 12 through Apollo 17, excluding Apollo 11's much simpler initial package, deployed a suite of instruments powered by a small plutonium-238 radioisotope thermoelectric generator, providing steady electrical power independent of sunlight, allowing the instruments to keep transmitting through the 2-week-long lunar night when solar power would have failed. The network eventually included seismometers at 4 separate sites, arranged with enough geographic spread across the lunar surface to allow scientists on Earth to triangulate the source and depth of seismic events using the same basic principle used to locate earthquakes on Earth. It also included heat flow probes drilled beneath the surface to measure how quickly heat escaped from the lunar interior, magnetometers to measure local magnetic field variations, and instruments to detect the thin, transient lunar atmosphere and any charged particles reaching the surface from the solar wind. This network operated continuously, transmitting data around the clock from 1969 until NASA made the decision to power it down in September 1977, a shutdown driven entirely by the same tightening budget environment that had already ended crewed lunar missions 5 years earlier, not by any failure or exhaustion of the instruments themselves, several of which were still functioning normally when the shutdown order came. Apollo 17 left the lunar surface on December 14, 1972, and no human being has returned since, a gap that has now stretched past 50 years, longer than the entire span of time separating the Wright brothers' first flight from Apollo 11 itself. Missions 18, 19, and 20 had been planned, funded hardware existed for at least some of them, and the program was canceled, not because it had failed, but officially because public and congressional interest in continued lunar exploration had declined sharply once the Cold War prestige objective had been achieved, and because the Nixon administration prioritized redirecting NASA's budget toward the Space Shuttle program instead. That is the accepted, well-documented, and almost certainly accurate historical explanation, and it deserves to be stated plainly as the leading account. It is also true that the abruptness of that ending, a program moving from 6 consecutive successful crewed landings straight into a 50-year hiatus with no immediate successor, has struck a number of researchers and commentators over the decades as a strange enough discontinuity to warrant its own questions. Questions this series will revisit later once we've examined exactly what the astronauts found, recorded, and, in some cases, said on the record and off it during those final missions. There is a military dimension to this story that deserves to be named directly because it is often glossed over in retrospectives that focus purely on exploration and heroism. The rocketry that carried Apollo to the moon descended in a very direct engineering lineage from Nazi Germany's V-2 ballistic missile program, and the man who led the Saturn V's development, Wernher von Braun, had been the technical director of that same V-2 program before being brought to the United States in 1945 under Operation Paperclip, a classified program that relocated German rocket scientists to American soil in the war's immediate aftermath, in some cases obscuring or minimizing their prior involvement with Nazi weapons production that had relied on forced concentration camp labor. Von Braun's team's expertise in large liquid-fueled rockets, developed originally to rain explosives on London, became the technological backbone of the American civilian space program within less than 2 decades, a transition that illustrates just how thin the line was. Throughout the entire era, between the rocket that could lift a spacecraft to the moon and the rocket that could deliver a warhead to an adversary's capital, every milestone in the space race, Sputnik, Gagarin's flight, Apollo itself, carried that dual meaning for the governments funding it, even when the public messaging emphasized only exploration and scientific discovery. The Soviet side of the race deserves more attention here than it typically receives in American retellings, because the Soviets were not merely a background threat that motivated American spending. They were running a parallel, genuinely competitive crewed lunar program of their own, built around a massive rocket called the N-1, roughly comparable in scale and ambition to the Saturn V. The N-1 suffered 4 catastrophic launch failures between 1969 and 1972, including one explosion that remains among the largest non-nuclear explosions in human history. And those repeated failures, combined with the death of the program's chief designer, Sergei Korolev, in 1966, ultimately forced the Soviet Union to abandon its own crewed lunar ambitions and quietly redirect its program toward robotic lunar exploration and later Earth orbit space stations instead. The Soviet lunar program's failure was not made public with anything like the openness of NASA's successes, and for years afterward, Soviet officials downplayed or denied that a crewed lunar program had ever been a serious priority at all, a pattern of selective disclosure that will become relevant again later in this series when we examine the very different way the Soviet space program handled the release of its own anomalous lunar findings compared to NASA's more public, if still selective, approach. Public enthusiasm for the program, worth noting here because it complicates the later cancellation, followed an uneven arc that rarely gets acknowledged. Kennedy's original commitment was, by several contemporary accounts, met with real skepticism among the American public and within Congress, skepticism Kennedy directly addressed in a follow-up speech at Rice University in September 1962, where he famously argued the country should choose to go to the moon specifically because the goal was difficult, framing the entire undertaking as a test of national will rather than a straightforward scientific proposal. Public support climbed through the mid-1960s as hardware began flying successfully, peaked overwhelmingly around the Apollo 11 landing itself, watched live by an estimated audience of roughly 600 million people worldwide, and then declined with striking speed. Gallup polling conducted in the years immediately following Apollo 11 found that a majority of Americans did not believe the program's cost was justified, and by the time of Apollo 17 in December 1972, network television coverage of the mission had been scaled back considerably compared to the wall-to-wall broadcasts of 1969, a reflection of an American public that had, in the space of just over 3 years, moved from treating lunar landings as a once-in-a-civilization spectacle to treating them as a routine, expensive government program competing for attention and funding against the Vietnam War and a range of expanding domestic social programs. It's worth pausing here to draw a clear line this series intends to hold to throughout, because this general subject area sits close to a very different and much better known conspiracy claim that has nothing to do with what we're examining. This series takes no position questioning whether the Apollo landings themselves happened. They did. The photographic record, the physical sample evidence, the independent tracking of the missions by observatories outside the United States, including Soviet ones, and the plain physics of the retroreflectors, still in use by astronomers today, make the moon landing hoax claim one of the more thoroughly and repeatedly disproven ideas in modern popular conspiracy culture. And this series has no interest in relitigating it. The question this documentary is built around is a different one entirely. Not whether humans reached the moon, which is not in serious doubt, but whether what those humans found once they got there has been fully and honestly explained. Those are two separate questions, and conflating them, as popular culture sometimes carelessly does a disservice to both. The later missions deserve individual mention because each contributed a specific piece to the puzzle this series is assembling. Apollo 15, in the summer of 1971, targeted the Hadley-Apennine region specifically for its geological diversity, and its crew, David Scott and James Irwin, recovered a sample that came to be known as the Genesis Rock, a piece of ancient lunar crust later dated to nearly 4.5 billion years old, among the oldest rock samples ever recovered from any world including Earth, whose own oldest surviving rocks were mostly recycled or destroyed by billions of years of plate tectonics. Apollo 16, in April 1972, was the only mission to land in the lunar highlands rather than the darker mare regions, specifically to test the hypothesis that the highlands were volcanic in origin, a hypothesis the mission's own samples ultimately disproved, revealing highland rock to be primarily impact-formed breccia rather than volcanic material, a genuine scientific surprise that reshaped models of the moon's early bombardment history. Apollo 17, the final crewed mission, flown in December 1972, carried the only professional geologist to ever walk on the moon, Harrison Schmitt, whose trained eye led directly to the discovery of orange-colored volcanic glass beads scattered across the Taurus Littrow Valley, the same beads that would later, in 2008, yield the water content discovery discussed in the previous part of this series. 6 successful crewed landings, roughly 840 pounds of returned lunar samples, a functioning seismic and geophysical instrument network that ran for the better part of a decade, and a body of first-hand human testimony and mission data that has never been fully superseded by any robotic mission flown since, Soviet, American, or Chinese. Everything this series examines from this point forward, the ringing seismic data, the hollow moon calculations, the photographic anomalies, the astronaut statements, traces back to that 6-mission, 3.5-year window between 1969 and 1972, and to the network of silent instruments the astronauts left running behind them when they climbed back into their ascent stages for the final time. That seismic network's very first major result came almost by accident, from a piece of equipment nobody had originally intended as a scientific instrument at all, the spent ascent stage of the Apollo 12 lunar module, deliberately flown back down into the lunar surface after its crew had returned safely to orbit. What the seismometers recorded when that piece of hardware struck the moon is where we turn next. and it is the single most frequently cited piece of evidence in this entire hypothesis, repeated in nearly every documentary, book, and article ever written about the possibility that the moon is hollow. The moon that rings like a bell. On November 20th, 1969, the ascent stage of the Apollo 12 lunar module, its job finished after safely returning astronauts Pete Conrad and Alan Bean to lunar orbit, was deliberately steered back down into the moon's surface, a standard piece of mission planning intended to generate a calibrated seismic signal for the instrument package the astronauts had left behind on the ground. The impact struck roughly 40 miles from that seismometer, releasing an amount of energy comparable to about 1 ton of TNT, a modest, entirely expected engineering event. What was not expected was what the seismometer recorded afterward. Instead of a sharp spike that faded quickly, the way an impact on solid rock should behave, the instrument traced out a signal that built gradually, peaked, and then diminished only slowly, continuing to register vibrations for close to an hour after the impact itself. The scientists monitoring the data back on Earth, led by the seismic experiment's principal investigator, Maurice Ewing, a geophysicist with decades of experience studying Earth's own seismic behavior, used a specific word to describe what they were seeing in their own technical write-ups and public statements. The moon had rung, they said, like a bell. That phrase was not a flourish added later by popular media, though it has certainly been repeated endlessly by popular media in the more than 5 decades since. It came from the mission scientists themselves, trying to describe an observation that genuinely surprised them because the behavior did not match what a solid, Earth-like rocky body should do when struck. On Earth, an impact of comparable energy produces a seismic signal that rises sharply and then decays within a matter of minutes because Earth's crust is a complex, layered structure saturated with water and organized into relatively coherent rock strata that absorb and dampen vibration efficiently as it passes through. The Apollo 12 signal did nothing of the sort. It behaved less like a struck rock and more like a struck bell or a tuning fork, continuing to reverberate long after any Earth-based equivalent would have gone silent. And it was that specific, almost musical quality of the decay curve that gave rise to the ringing description in the first place. NASA did not treat this as a one-time curiosity. The result was interesting enough and useful enough for understanding the moon's interior that mission planners built deliberate impact tests directly into the remaining Apollo flight plans, turning spent hardware that would otherwise have simply drifted in space or burned up on re-entry into calibrated seismic sources. Beginning with Apollo 13 in April 1970, the massive third stage of the Saturn V rocket itself, the SIVB stage, weighing many times more than a lunar module ascent stage, was deliberately targeted to impact the lunar surface after completing its job of pushing the spacecraft toward the moon, rather than being discarded into a harmless solar orbit as earlier missions had done. The Apollo 13 SIVB impact released energy equivalent to roughly 11 tons of TNT, more than 10 times the energy of the Apollo 12 lunar module impact, and the resulting seismic signal, detected by the seismometer left behind by the earlier Apollo 12 crew since Apollo 13 itself never landed, reverberated for over 3 hours, registering at a seismic station more than 80 miles from the impact point. Later missions repeated the pattern. Apollo 14, 15, 16, and 17 each contributed additional deliberate impacts from both spent SVB stages and, where applicable, spent lunar module ascent stages, building up a small but carefully calibrated catalog of artificial moonquakes whose exact energy, timing, and impact location were known with precision, a controlled experiment no natural earthquake on our own planet could ever offer seismologists. This is the point where the mainstream scientific interpretation and the alternative interpretation begin to genuinely diverge, and it is worth laying out the mainstream explanation in full detail before addressing the alternative, because the mainstream account is more specific and more grounded in comparative planetary geology than it is often given credit for in popular retellings. The explanation geophysicists settled on and have continued to refine in the decades since through both further Apollo-era analysis and more recent modeling centers on a property of the moon's outer layers called scattering. Earth's crust, layered, water-saturated, and continuously reworked by plate tectonics, transmits seismic energy in a relatively organized way, with distinct boundaries between rock layers that seismic waves cross cleanly, losing energy steadily and predictably as they travel, which produces the sharp, quickly decaying signal we're used to from earthquake recordings. The moon's outer layers are a fundamentally different kind of material, billions of years of relentless meteorite bombardment, entirely unmitigated by an atmosphere thick enough to burn up incoming debris and unhealed by any process resembling plate tectonics, has pulverized the moon's upper crust into what geologists call a megaregolith, a deep layer of shattered, fractured, structurally chaotic rock riddled with cracks, voids, and boundaries at every conceivable scale, extending kilometers beneath the surface in a way Earth's comparatively young, water-smoothed, and tectonically refreshed crust never develops. When a seismic wave enters a medium that chaotic, it does not travel cleanly from source to sensor the way it does through Earth's more orderly layers. It scatters, bouncing unpredictably off countless internal boundaries, taking wildly varying and elongated paths to reach the same detector, arriving not as a single coherent pulse but as a long, smeared-out train of arrivals spread across a much longer window of time. Combine that scattering effect with the total absence of water, which on Earth plays a significant role in damping seismic energy as it passes through saturated rock, and you get a medium that transmits seismic energy inefficiently in terms of clean signal propagation, but very efficiently in terms of how long that energy continues bouncing around before it finally dissipates. The result, according to this explanation, is exactly the kind of long, slowly decaying, ringing signal the Apollo seismometers recorded, produced not by a hollow interior acting as a resonant chamber the way the inside of an actual bell does, but by a chaotically fractured, bone-dry outer layer scattering seismic energy across a much longer timescale than Earth's crust ever would. This scattering-based explanation has been the dominant geophysical interpretation since the 1970s, refined by decades of subsequent modeling, and it does not require or particularly support the idea of a large empty cavity inside the moon at all. That is the mainstream case, stated as strongly and specifically as the evidence allows. The alternative interpretation, advanced by hollow moon researchers beginning with Vassin and Scherbakov's 1970 paper and developed in far more mathematical detail by later writers, including Don Wilson, does not dispute the scattering explanation outright so much as argue that it does not, by itself, rule out an additional structural contribution, and that the sheer duration and character of some of the recorded signals, particularly the Apollo 13's Ivo-B event, exceed what a purely scattering-based model would predict for a solid, if fractured, body. We will examine that specific mathematical argument in close detail in the next part of this series, because it deserves a full and fair hearing on its own terms, rather than a summary compressed into a single paragraph here. What matters for this part is understanding, clearly, that both explanations start from the same undisputed raw data. Nobody disputes that the moon rang. What is disputed, and what remains genuinely disputed in certain corners of the technical literature even today, is exactly how much of that ringing is fully explained by megaregolith scattering alone, and how much, if any, residual behavior in the data might point towards something in the moon's deep internal structure that the scattering model has not yet fully accounted for. Morris Ewing, the scientist most closely associated with the Apollo seismic program and its early public description of the moon's ringing, was not a newcomer prone to sensational language. He had spent decades before Apollo establishing himself as one of the 20th century's most respected geophysicists, having pioneered seismic refraction techniques used to map the ocean floor, and having played a central role in the evidence that helped confirm plate tectonics as a description of how Earth's crust actually moves. When a scientist, with that kind of institutional standing and that kind of track record for careful, conservative interpretation of seismic data, chose the word ringing to describe what the Apollo 12 instrument had recorded, it carried a different weight than the same word would carry coming from someone less established, and that credibility is a meaningful part of why the phrase entered the historical record with such staying power, rather than being quietly revised away in later, more cautious follow-up papers. The specific numbers from each mission's deliberate impacts are worth laying out individually, because the pattern across missions, not just the headline Apollo 12 result, is what gives the dataset its scientific weight. Apollo 14's SIVB stage struck the surface in January 1971, generating a signal that lasted well over an hour, detected across multiple stations of the growing seismic network. Apollo 15's spent SIVB impact in July of that year produced a similarly extended signal, and the mission also contributed a lunar module ascent stage impact once its crew safely departed the surface, giving seismologists two independent artificial events from the same flight to compare directly against one another. Apollo 16 and Apollo 17 each repeated the pattern through the final months of the crewed program in 1972, by which point NASA's seismic team had accumulated enough calibrated impact data, precise mass, precise velocity, precise location, and precisely measured seismic response to begin building genuine quantitative models of how energy propagated through the moon's outer layers, rather than relying on qualitative description alone. That accumulated dataset, 5 known artificial impacts of carefully documented energy struck against the same general seismic network over a span of about 3 years, remains, more than half a century later, the single richest body of calibrated impact seismology data ever collected on any body besides Earth. It is worth comparing that Apollo-era lunar data against what a very different world has since revealed about seismic behavior elsewhere in the solar system, because the comparison sharpens exactly how unusual the moon's response really is. NASA's InSight lander touched down on Mars in November 2018, carrying a dedicated seismometer that operated on the Martian surface for roughly 4 years, recording well over 1,000 Marsquakes before the mission concluded in 2022. Mars, like the Moon, lacks Earth's active plate tectonics and has a comparatively dry crust, and Martian seismic signals do show somewhat longer decay times than equivalent events on Earth, consistent with the same general scattering principle described earlier in this part. But even Mars's seismic signals decay considerably faster than the Moon's most extreme recorded ringing events, suggesting that whatever combination of dryness, crustal fracturing, and internal structure produces the Moon's specific seismic signature is not simply a generic property of any dry, tectonically quiet rocky world, but something more specific to the Moon's own particular internal condition, a detail that keeps the door open, at least slightly, for continued scientific interest in exactly what makes the Moon's case as extreme as it is, even among mainstream researchers who fully accept the megaregolith scattering explanation as the primary driver. It is also worth being precise about how the ringing description has traveled since 1969, because the gap between what NASA's own scientists actually documented and what popular culture eventually did with that documentation is itself instructive. Ewing and his colleagues' original technical write-ups describe a specific, quantifiable seismic decay pattern, unusual, genuinely surprising, and worth flagging prominently in their published results, but framed throughout as a property of the Moon's outer material behavior, not as direct evidence of a hollow or artificial structure. That framing held for the first several years after the discovery, discussed within the geophysics community primarily as a puzzle about crustal composition. It was Vassin and Shcherbakov's 1970 paper, and considerably more so Wilson's 1975 book, that took the raw, rang like a bell phrase, already vivid and quotable on its own terms, and built it into the centerpiece of a fully developed hollow moon argument aimed at a general audience rather than a specialist one. From there, the phrase spread through decades of documentaries, books, and eventually internet content, frequently stripped of the qualifying detail that the same scientists who first described the ringing never claimed. It proved a hollow interior and frequently paired with the vivid, intuitive, but scientifically imprecise comparison to striking an actual hollow bell versus striking a solid rock, an analogy that is rhetorically powerful but does not map cleanly onto the actual physics of seismic wave scattering through a fractured, heterogeneous megaregolith, which can produce long reverberation times without requiring any large-scale interior cavity at all. Once operational, the 4-station seismometer array, running continuously from 1969 until its 1977 shutdown, began detecting a steady stream of naturally occurring seismic events entirely independent of any human-caused impact, and the classification of those natural events turned out to be nearly as strange as the ringing itself. Lunar seismologists eventually sorted the network's detections into 4 broad categories. Deep moonquakes, the most common type by a wide margin, originate from roughly 700 kilometers below the surface, far deeper than most earthquakes on our own planet, and occur in a pattern tightly correlated with the moon's monthly orbital cycle, strongly suggesting they are triggered by the same tidal stresses Earth's gravity exerts on the moon that we discussed back in the first part of this series, flexing and stressing rock deep within the lunar interior as the moon's distance from Earth varies slightly across each orbit. Meteoroid impact quakes, the second category, are exactly what they sound like. Natural impacts from small space debris striking the surface, providing a useful natural counterpart to the artificial impacts astronauts staged deliberately. Thermal moonquakes, the third category, are triggered by the moon's brutal temperature swings between its 2-week-long day and 2-week-long night, a difference exceeding several hundred degrees Fahrenheit that causes surface rock to expand and contract enough to crack and shift audibly to the seismometers, most commonly detected right around lunar sunrise as the surface begins rapidly heating after 2 weeks of extreme cold. The fourth category, shallow moonquakes, is the one that has generated the most sustained scientific interest and the most sustained uncertainty, originating much closer to the surface than the deep tidal quakes. Typically within a few dozen kilometers of the lunar crust, shallow moonquakes are comparatively rare in the Apollo-era catalog, but disproportionately powerful, with some recorded events estimated at magnitude 5 or higher on a scale comparable to the one used for earthquakes on Earth, strong enough that a similarly sized event on Earth would cause real structural damage to nearby buildings. Unlike the deep moonquakes, shallow moonquakes show no clear correlation with the lunar tidal cycle, and their precise triggering mechanism remained essentially unexplained throughout the Apollo era and for decades afterward, an acknowledged, published gap in the geophysical understanding of a body most people assume was fully mapped and explained by the missions that first walked on it. One particular shallow moonquake, recorded in 1975 near the end of the network's operational life, registered strongly enough on the seismometers to draw special attention from researchers reviewing the archived data years later. Its epicenter estimated close enough to existing surface imagery that later analysts cross-referencing the event began specifically searching nearby terrain for a visible surface cause, a search that would eventually connect to the fault scarp discovery described below, though that connection took decades to establish. Across the full Apollo seismic catalog, several dozen shallow events were eventually identified, a small enough sample that building a confident statistical picture of their distribution, depth, and triggering mechanism from Apollo-era data alone was simply not possible, which is precisely why the mystery persisted, unresolved but not forgotten, in the specialist literature for as long as it did. That gap did not close until well into the era of renewed robotic lunar exploration. In 2019, a team of researchers led by Thomas Waters, analyzing high-resolution imagery collected by NASA's Lunar Reconnaissance Orbiter, which has been mapping the moon in unprecedented detail since 2009, published findings in the journal Nature Geoscience linking a cluster of the original Apollo-era shallow moonquakes to a system of previously undetected young fault scarps, cliff-like ridges in the lunar surface formed as the moon's interior slowly cooled pulls and contracts, causing its solid crust to buckle and fracture, much the way the skin of a grape wrinkles as it dries into a raisin. The freshness of these scarps, judged by the sharpness of their edges and the near-total absence of the small overlapping crater impacts that gradually erode and soften older lunar terrain, indicated they had formed recently by geological standards, and the correlation with recorded shallow moonquake epicenters suggested the moon remains tectonically active today, still slowly shrinking and fracturing its crust in measurable, ongoing events, rather than being the completely geologically dead world it had been assumed to be for most of the decades following Apollo. This finding did not come from a fringe source. It came from mainstream NASA-funded research, published in a mainstream peer-reviewed journal, and it fundamentally revised what planetary scientists thought they understood about a subject the Apollo program had supposedly already closed the book on nearly 50 years earlier. That revision matters for how we should read the rest of this series. It demonstrates, using data entirely outside the disputed territory of hollow moon claims, that the Apollo seismic record was not fully understood even by mainstream science for decades after it was collected, and that meaningful new interpretations of that same 40-year-old data continue to emerge as better tools, better imagery, and better analytical techniques become available. If shallow moonquakes could go unexplained for nearly half a century before a satisfying mainstream mechanism was finally identified, it becomes harder to dismiss out of hand the possibility that other unresolved features of the same seismic record, including the specific character and duration of the artificial ringing events, might likewise be sitting on interpretations that have not yet been fully worked out, whether those eventual interpretations turn out to be exotic or, as is more often the case in the history of this kind of unresolved data, simply more mundane than anyone currently expects. The 2019 fault scarp findings have themselves become part of the alternative literature in the years since their publication, cited by some hollow moon researchers and their online successors not as evidence against the hypothesis, but as fresh confirmation that mainstream science continues to be surprised by the moon's internal behavior decades after supposedly settling the question. That reading stretches the actual finding considerably. Waters and his colleagues' published conclusion was specifically that the moon's crust is cooling and contracting, a process consistent with a solid or near-solid body slowly losing residual heat from its formation, the same basic mechanism that produces contraction cracking in cooling lava and, on a much larger scale, in cooling planetary crusts generally. A contracting solid interior is, if anything, harder to reconcile with a large hollow cavity than a static one would be, since a genuinely hollow structure would not be expected to generate the kind of steady, planet-wide contractile stress the fault scarps appear to record. This is a useful example of a pattern worth watching for throughout the rest of this series. A legitimate scientific surprise, reported honestly in a mainstream journal, being absorbed into the alternative literature as general-purpose evidence of official uncertainty, regardless of whether the specific finding actually points in the hollow moon hypothesis's favor, or, as in this case, points more naturally in the opposite direction. None of this, on its own, proves the moon is hollow, artificial, or occupied. What it establishes, cleanly and without exaggeration, is that the moon's seismic behavior is genuinely unusual compared to Earth's, that mainstream science has a coherent and reasonably well-supported explanation for the bulk of that unusual behavior rooted in the moon's shattered, dry outer crust, and that meaningful uncertainty about the fine details of that behavior has persisted, and in some cases only recently been resolved, well beyond the Apollo era itself. That is the state of the evidence as recorded seismic data. What we turn to next is the far more ambitious argument built directly on top of that data, the specific hypothesis, advanced first by Vossen and Shcherbakov, and expanded considerably by later researchers, that the moon's overall density, its internal mass distribution, and yes, its seismic ringing, are not simply unusual, but are collectively consistent with a body that is not solid rock at all the way it should be, but partially or substantially hollow, potentially engineered rather than accreted. That argument deserves its own full and careful examination on its own mathematical terms, and that is exactly where we turn next. The hollow moon hypothesis. Strip away the seismic ringing for a moment, and there is a simpler, more fundamental number that started this entire line of thinking decades before Apollo ever reached the surface. The moon's average density. Earth's average density, calculated from its total mass divided by its total volume, works out to about 5.5 grams per cubic centimeter. The moon's average density is only about 3.33 grams per cubic centimeter, roughly 60% of Earth's. That difference alone is not unusual or alarming. It is exactly what you would expect from a smaller body with proportionally less internal pressure compressing its interior material, and less overall iron content relative to its size, both of which the giant impact hypothesis, examined a few parts back, specifically predicts. But the specific number, 3.33 grams per cubic centimeter, sits close enough to the density of ordinary rock, roughly 3 grams per cubic centimeter for typical silicate material, that it leaves comparatively little room for a large, dense metallic core of the kind Earth has. And this is precisely the observation Mikhail Vasin and Alexander Shcherbakov built their argument around in their 1970 paper for Sputnik magazine. Their reasoning proceeded roughly as follows, and it is worth walking through it in the same sequence they presented it, because the logic, whatever you ultimately conclude about its strength, is more structured than the popular summary of "the moon is hollow because it's less dense" usually credits it with being. A body formed through ordinary accretion, they argued, condensing gradually from a disk of dust and debris under the simple pull of its own gravity, should settle into a layered structure with progressively denser material toward the center, driven by heavier elements like iron sinking through the still molten interior during the body's early hot formation phase, a process called differentiation that both Earth and we now understand more precisely than Vasin and Shcherbakov could have in 1970, the moon itself actually underwent. Given the moon's overall size and gravity, they calculated that a fully solid, naturally differentiated body of the moon's dimensions should produce an average density measurably higher than the 3.33 grams per cubic centimeter actually observed, closer to what a rocky body with an Earth-like proportion of dense core material would produce. To account for the discrepancy, they proposed an alternative structural model. Rather than a solid body with a modest, dense core, the moon might be constructed with a comparatively thin outer shell, which they estimated, based on the density math available to them at the time, at roughly 20 miles thick, encasing a much larger interior volume that was either empty or filled with material considerably less dense than solid rock, bringing the overall average density down to match what was actually measured. It is important to be precise about what Vasin and Shcherbakov actually proposed, because later popular treatments, including some documentaries and books that followed in Wilson's wake, have flattened their argument into a simpler and stranger claim than the original paper made. They were not simply asserting that the moon is a giant empty ball. Their specific proposal, laid out with genuine engineering vocabulary reflecting their professional backgrounds, described a structure closer to a spacecraft hull, an outer shell of processed, structurally reinforced material, potentially incorporating metals given the paper's references to titanium and other refractory elements detected in returned lunar samples, surrounding an interior that could house machinery, storage, or living space, in essence describing the moon as a colossal constructed vessel rather than a naturally accreted planetary body. They connected this structural claim to two other pieces of evidence available to them by 1970, the unexpectedly low overall density we've just walked through, and the newly reported Apollo 12 seismic ringing, published only months before their own paper went to print, which they interpreted, as we discussed in the previous part of this series, as consistent with a body possessing significant internal void space rather than being solid throughout. To that, they added a third argument based on the unusual abundance of certain refractory metals, elements with very high melting points that are difficult to process without advanced technology, identified in the Apollo 11 and Apollo 12 sample analyses, arguing that concentrations of materials like titanium at the levels reported were more consistent, in their view, with processed or refined material than with the raw, unrefined composition a naturally accreted body should display. That third argument, the refractory metal claim, has aged the least well of the three, and it is worth addressing directly rather than leaving it hanging as though it remains an open question. Later, far more extensive geochemical analysis of the full Apollo sample collection, conducted over the decades since 1970 with instruments considerably more sensitive than anything available when Vasson and Shcherbakov were writing, established that the moon's titanium content, while genuinely higher in certain mere basalt samples than in typical Earth rock, falls within the range explainable by ordinary igneous differentiation processes, the same basic chemistry that concentrates certain elements in specific rock types on Earth through purely natural volcanic and crystallization processes, requiring no refining or processing by any intelligent agent. This is not a contested point within modern lunar geochemistry. The elevated titanium in certain lunar basalts is now well understood as a natural product of how the lunar magma ocean crystallized in its early history, with different minerals forming and settling out of the cooling magma at different stages, concentrating titanium-bearing minerals like ilmenite in specific rock layers that later erupted onto the surface as the dark mare basalts visible from Earth. Vasson and Shcherbakov were working from a genuinely limited 1970 dataset, barely a year removed from the first sample returns, and the specific chemical argument they built on top of that limited data has been superseded by the far more complete geochemical picture assembled in the decades since. It is worth noting, too, that Wilson's 1975 book, which did more than the original Soviet paper to popularize the hollow moon hypothesis in the English-speaking world, added its own supplementary arguments beyond simply repackaging Vasson and Shcherbakov's original case, and not all of those additions have aged any better than the refractory metal claim. Wilson pointed to the discovery of mascons themselves, only recently reported at the time of his writing, as further evidence of buried structure, and speculated more explicitly than the original Soviet paper had about the possibility that specific craters showing unusual circularity or wall regularity might mark engineered access points or ventilation structures rather than ordinary impact scarring. These specific claims did not hold up well against later, far more detailed orbital imagery. High-resolution mapping conducted by missions including the Lunar Reconnaissance Orbiter, which has photographed the entire lunar surface at resolutions fine enough to make out features the size of a small car in some locations, found the craters Wilson singled out to display exactly the kind of natural variability in wall slope, in ejecta pattern, in secondary cratering that ordinary impact processes reliably produce, with none of the specific candidate sites showing structural or material anomalies distinguishable from any other crater of comparable size and age. Wilson's book remains historically significant as the vehicle that carried the hollow moon hypothesis to a mass audience, but its specific supplementary claims have fared considerably worse under later scrutiny than the original density and seismic arguments it was built around. The density argument, however, deserves a more careful hearing because it connects to a body of measurement considerably more rigorous than anything available in 1970, and because the mainstream answer to it is genuinely interesting rather than dismissive. Modern lunar science does not deny that the moon's density is lower than a simple, uniform, Earth-like composition would predict. It offers a specific, measured explanation for why, built from data collected across the full span of lunar exploration from Apollo through the modern Grail mission. The moon's low overall density, in the mainstream model, does not come from a hollow interior. It comes from the combination of an unusually small metallic core, discussed in an earlier part of this series, at roughly 20% of the moon's radius, compared with the 55% core radius fraction Earth possesses, and an unusually thick crust made of low-density material, primarily a rock type called anorthosite, formed when lighter minerals crystallized out of the moon's early global magma ocean and floated to the surface the way ice floats on water, while denser material sank toward the core. Anorthosite is genuinely light for a rock, with a density around 2.9 grams per cubic centimeter, and the moon's crust, particularly in the ancient highland regions, is thick, in places estimated at several dozen kilometers, meaning a substantial fraction of the moon's total volume consists of this comparatively light surface material rather than denser mantle or core rock. Combine a proportionally tiny, low-mass fraction core with a thick shell of unusually light crustal rock, and the resulting average density, calculated from a solid, fully accounted for internal structure with no cavities required, lands very close to the 3 1/3 grams per cubic centimeter actually measured, without needing to remove any mass from the interior at all. There is a further, more technical piece of evidence that bears directly on the hollow moon claim, one that goes beyond simple average density and gets at the moon's actual internal mass distribution with much greater precision, a measurement called the moment of inertia factor. This value, derived from a combination of lunar laser ranging data collected using the retroreflectors the Apollo astronauts left on the surface, and from precise gravity field mapping performed by orbiting spacecraft including Grail, describes how the moon's mass is distributed relative to its center, essentially quantifying whether mass is concentrated toward the core, spread evenly throughout, or concentrated toward the surface. A perfectly uniform sphere, with identical density from center to surface, has a theoretical moment of inertia factor of exactly 0.4. A body with mass concentrated toward its center, like Earth with its dense iron core, has a factor measurably below 0.4. A body that was hollow, or had its mass concentrated disproportionately in a thin outer shell rather than at depth, would show a factor measurably above 0.4, since a shell structure holds its mass farther from the center of rotation than a uniformly filled sphere does. The moon's measured moment of inertia factor, refined progressively through decades of increasingly precise tracking data and now established with considerable confidence, comes out to approximately 0.393, slightly below the uniform sphere value, indicating a small but real concentration of mass toward the center, consistent with the small, dense core the mainstream model describes, and specifically inconsistent with a hollow or thin-shelled structure, which would be expected to produce a factor measurably above, not below, the uniform baseline. This is, in the view of the great majority of planetary scientists who have examined the question, close to a decisive piece of evidence against a literal hollow moon in the specific structural sense Vassin and Shcherbakov proposed. A moment of inertia factor below the uniform sphere value is difficult to reconcile with any model involving a large-scale, low-mass or empty interior region, because removing mass from the center of a sphere while keeping the same total mass and radius necessarily pushes the remaining mass outward toward the surface, driving the factor upward, not downward. The measured moon does the opposite of what a hollow model predicts. It is worth stating plainly that this measurement, unlike some of the more ambiguous evidence covered elsewhere in this series, is not something hollow moon proponents have offered a widely accepted counter-explanation for. It stands, largely unaddressed in the alternative literature, as one of the stronger data-driven challenges to the hypothesis in its original, literal form. It is also worth understanding what happened to the Vassin-Shcherbakov paper within the Soviet scientific establishment itself, because that reception has often been mischaracterized in Western retellings, eager to cast it either as a suppressed state secret or as an official Soviet government position. Neither framing holds up well. Sputnik magazine, despite its state-sanctioned publication, was explicitly a popular science and culture outlet rather than a peer-reviewed research journal, comparable in its function to Western general-interest science magazines of the era, and its publication of the Vassin-Shcherbakov argument reflected an editorial judgment that the idea was interesting and provocative enough for a general readership, not an endorsement from the Soviet Academy of Sciences or any formal research institution. Soviet planetary scientists working within the country's own lunar research programs, including those directly involved in the lunar robotic missions we will examine in more detail later in this series, did not adopt the hollow moon hypothesis as a working model, and mainstream Soviet astronomy proceeded through the 1970s along essentially the same differentiated body framework that Western science was independently converging on. The paper's lasting influence came almost entirely through its Western reception, particularly once Don Wilson incorporated it into his considerably more widely read 1975 book, rather than through any specific weight it carried within Soviet science itself. The practical consequences of the Mascon discovery for the Apollo program deserve a bit more attention than a passing mention because they illustrate just how immediately consequential this originally obscure gravitational anomaly turned out to be. When Muller and Sjogren identified the unexpected velocity changes in lunar orbiter tracking data in 1968, NASA's own navigation teams initially worried the anomalies might reflect equipment or tracking errors rather than a genuine feature of the moon's gravity field, since nothing in existing models predicted gravitational irregularities of that scale. Confirming that the anomalies were real and mapping them precisely enough to be factored into descent trajectory calculations became an urgent practical priority once crewed landings were scheduled, because an unaccounted-for gravitational tug strong enough to measurably alter an orbiting spacecraft's velocity was also strong enough to meaningfully affect a lunar module's automated descent path, introducing exactly the kind of last-minute guidance error that very nearly diverted Apollo 11 into the boulder field discussed several parts back. Later, Apollo missions incorporated Mascon data directly into their descent guidance software, a detail that underscores just how quickly an anomaly discovered almost by accident, through nothing more than careful tracking of small velocity fluctuations, became operationally essential to landing astronauts safely on the surface. That leaves the Mascons, and this is where the picture becomes genuinely more complicated and genuinely more interesting than either the strongest hollow moon claims or the simplest mainstream dismissals fully capture. Mascons, short for mass concentrations, were discovered in 1968 by NASA scientists Paul Muller and William Sjogren, who noticed that spacecraft orbiting the moon experienced small, repeated, unexplained changes in velocity as they passed over specific regions, particularly over the large circular mare basins like Imbrium, Serenitatis, and Chrysium, speeding up slightly as they approached these regions and slowing again as they passed beyond them, a signature indicating pockets of unusually concentrated mass and therefore unusually strong local gravity sitting beneath those specific surface features. This discovery genuinely surprised the scientists who made it, and it genuinely complicated early spacecraft navigation planning for the crewed Apollo missions that followed, since accurate landing required accounting for these unexpected gravitational irregularities. The mainstream explanation for most Mascons, developed over the years following their discovery, holds that they represent dense basaltic lava that flooded ancient impact basins after enormous asteroid or comet strikes billions of years ago, cracked the moon's crust deeply enough to allow magma from the interior to well up and fill the resulting depression, cooling into the dark, iron-rich basalt that gives the Maria their distinctive dark coloring visible from Earth even without a telescope. Because this basaltic infill is measurably denser than the surrounding highland crust, the filled basins register as localized zones of excess mass, exactly the gravitational signature Muller and Sjogren detected. This explanation accounts well for the largest, most obvious Mascons, correlating tightly with the largest visible Maria, and it remains the dominant explanation for that category of Mascon today. But it is not the complete picture, and mainstream lunar science itself has acknowledged as much since the far more detailed gravity mapping performed by the Twin Grail spacecraft in 2011 and 2012, which measured the moon's gravitational field with a precision orders of magnitude beyond what Apollo-era tracking could achieve. That mission, published in a series of papers in the journal Science in 2013, revealed a considerably larger population of Mascons than previously known, including smaller Mascons associated with craters that show no visible basaltic mare filling at all, a category the simple lava infill explanation does not directly account for. For those unfilled craters, researchers led by planetary scientist J. Melosh proposed a different, more geometrically specific mechanism involving the way large impacts briefly liquefy and then re-harden the deep crust beneath a crater, combined with the slow post-impact settling and structural relaxation of the crater's rim and central peak, together producing a distinctive bullseye pattern of alternating dense and less dense material that Grail's finer resolution was able to detect for the first time. This is a legitimate, still developing area of active research, genuinely more complex than either the simplest lava infill explanation or the simplest hollow moon alternative fully captures, and it stands as a good example of the kind of nuance this series is committed to including, rather than smoothing over. Not every mascon is explained by exactly the same mechanism, and mainstream planetary science continues to refine its understanding of precisely how these features form, even as the overall body of evidence, from moment of inertia measurements to detailed impact basin modeling, continues to weigh heavily against the specific large-scale hollow interior that Vassin and Shcherbakov originally proposed. The Grail mission's broader gravity map, beyond the mascons specifically, also gave scientists their first truly detailed look at how the moon's crustal thickness varies across its entire surface. And that map turned up an asymmetry worth flagging here because it will matter considerably more in a later part of this series dealing with the lunar far side. The crust on the moon's near side, the hemisphere permanently facing Earth, is measurably thinner on average than the crust on the far side, in places by a factor of 2 or more, a difference substantial enough that it directly affects where volcanic mare basalt was able to reach the surface at all across the moon's early history, largely explaining why the near side is peppered with the large, dark maria visible from Earth, while the far side is dominated almost entirely by lighter, ancient highland terrain with only scattered, much smaller patches of mare material. Mainstream explanations for this asymmetry involve differences in the distribution of heat-producing radioactive elements between the two hemispheres, and possibly the lingering thermal effects of a proposed second, smaller impact early in the moon's history, sometimes called the Giant Impact Companion or Big Splat hypothesis. It remains, along with the fine details of individual non-mare mascons, one of the genuinely open structural questions in modern lunar geophysics, and we will return to it directly once this series reaches the far side itself. Where does that leave the hollow moon hypothesis in its most literal and original form, after weighing the density argument, the moment of inertia measurement, and the mascon data against it? The honest answer, and the one this series intends to give you rather than a more dramatic alternative, is that the specific, literal version of the hypothesis, a moon with a large, mostly empty interior enclosed by a thin structural shell, faces serious, largely unaddressed quantitative difficulties, most significantly, the moment of inertia measurement, that have not been satisfactorily answered by proponents of the hypothesis in the more than 5 decades since it was first proposed. The low average density and the seismic ringing that originally motivated Vassin and Shcherbakov's argument both have coherent, evidence-supported mainstream explanations that do not require an empty interior, explanations refined and strengthened considerably by data the two original authors did not have access to in 1970. That does not make every question surrounding the moon's interior fully closed, as the ongoing mascon research and the recent fault scarp discoveries covered in the previous part of this series both demonstrate. But the specific literal hollow moon claim, as originally formulated, sits on considerably weaker ground today than the density and seismic numbers alone made it appear to sit on more than 50 years ago. That does not end the broader inquiry this series is built around, and it would be a mistake to treat the hollow moon hypothesis's specific structural claims as the entirety of the case for an artificial or observed moon. What remains, once the density and seismic arguments have been weighed as carefully as we've just weighed them, is a different category of evidence entirely, evidence that does not depend on what is or is not inside the moon, but on what has been seen happening on its surface, recorded not by spacecraft instruments but by human eyes through telescopes across 4 centuries of careful astronomical observation. That evidence, known collectively as transient lunar phenomena, brief flashes, glows, and color changes reported at specific lunar locations by professional and amateur astronomers alike, since well before the space age began, is where we turn next. Lights in the dark, The moon is supposed to be dead, not biologically dead in the sense of never having hosted life, which is a separate and largely settled question, but geologically dead, a cooled, inert, airless rock with no ongoing internal activity, capable of producing light, motion, or change on any timescale a human observer could witness within a single lifetime, let alone within a single night. That assumption underlies almost everything in modern popular understanding of the moon, and it makes the subject of this part all the more striking because it is not an assumption shared by the historical observational record. For close to 900 years, astronomers, from untrained monks squinting at the sky without optical aid to professionally trained observers working with world-class telescopes, have reported seeing something happen on the lunar surface. Brief flashes, localized glows, temporary reddish or bluish discolorations, and moments where familiar surface features appeared to blur, brighten, or briefly vanish. Phenomena collectively known today as transient lunar phenomena, or TLP. The earliest widely cited account comes from an English chronicler named Gervase of Canterbury, who recorded in a monastic chronicle dated to the year 1178 that a group of monks observing the crescent moon reported watching its upper horn split with what the account describes as a flaming torch, or sparks, fire, and glowing coals spewing from the point of separation, an event vivid and specific enough that the account has been debated by historians and astronomers for centuries since. In the 1970s, a theory emerged connecting this account to a large, extremely young-looking crater called Giordano Bruno, located on the lunar far side and notable for its unusually fresh, bright ray system, unfaded by the billions of years of slow space weathering that dulls older craters, suggesting a comparatively recent formation. The idea that the Canterbury monks might have witnessed the actual impact that created Giordano Bruno captured public imagination for years, but it has since been substantially undermined by subsequent analysis. An impact large enough to produce a crater of that size striking the moon would be expected to eject enough debris into Earth-crossing space to trigger a significant, days-long meteor shower as that ejected material entered Earth's atmosphere, and no historical record from anywhere in the well-documented astronomical traditions of the period, Arab, Chinese, or European, describes any such shower around 1178. Most planetary scientists today consider it far more likely that Gervase's monks witnessed something more mundane, possibly a meteor burning up in Earth's own atmosphere, positioned by chance in the same line of sight as the moon, an optical effect entirely unrelated to the lunar surface itself, though the specific event they described has never been definitively identified nearly 9 centuries later. The observational record becomes considerably more credible and considerably more difficult to dismiss once it moves into the era of skilled, telescope-equipped professional astronomers keeping careful written notes. William Herschel, the German-born British astronomer credited with discovering the planet Uranus and one of the most accomplished observers of his era, recorded seeing reddish glowing points on the unilluminated portion of the moon on multiple occasions in 1783 and again in 1787, specifically near a bright, prominent crater called Aristarchus, describing what he interpreted at the time as possible volcanic activity. Herschel was not a careless or credulous observer. His technical skill and the quality of his instruments were, for the period, without serious peer, and his willingness to record and publish an observation that fell so far outside the expected behavior of an inert lunar surface carries real weight precisely because of how methodical he was known to be in every other area of his astronomical work. Herschel was far from alone among serious historical observers. The Reverend T.W. Webb, a respected 19th century English astronomer whose observational guides remained standard references for amateur astronomers well into the 20th century, documented multiple instances of anomalous lunar coloration in his own logs. In 1866, another experienced observer, Julius Schmidt, director of the Athens Observatory, created a stir within the astronomical community when he reported that a small crater called Lunar, which earlier lunar cartographers had mapped as a distinct, well-defined crater, appeared to have changed in character, now showing as a shallow, indistinct depression surrounded by a light patch rather than the sharper feature shown in earlier charts. Schmidt's claim that a lunar surface feature had physically changed within a matter of decades triggered a genuine scientific controversy at the time, since the entire prevailing assumption of lunar geology held that nothing on the airless, presumably inert surface should be capable of changing on a human observational timescale at all. Later, more careful comparison of the original charting techniques used by earlier astronomers concluded that the discrepancy most likely reflected differences in drawing precision and lighting conditions between observations, rather than an actual physical change to the crater. But the Linné controversy is historically significant, regardless of its ultimate resolution, because it forced the astronomical establishment of the period to seriously engage, for perhaps the first time in a formal public way, with the question of whether the moon might not be as permanently static as everyone had simply assumed it to be. It is also worth addressing directly one of the more credible skeptical explanations for a meaningful portion of the pre-20th century TLP catalog, because a fair treatment of this subject requires taking the strongest counterarguments seriously rather than only the strongest supporting evidence. Many historical telescopes, particularly the simple refracting instruments in common use through the 18th and much of the 19th century, suffered from a well-documented optical defect called chromatic aberration, in which a lens fails to focus all wavelengths of light to exactly the same point, producing faint-colored fringes, often reddish or bluish, around bright objects viewed at the edge of the field or under certain focus conditions. Given that the moon is an extremely bright object, typically viewed against a dark sky, exactly the kind of high-contrast target most likely to reveal this specific optical flaw, some fraction of historical reports describing reddish or bluish coloration on the lunar surface, including possibly some of Herschel's own observations made with the instruments available to him in the 1780s, may reflect an artifact of the observer's own equipment, rather than anything happening on the moon itself. Modern professional telescopes, built with compound lens systems and reflecting optics specifically designed to correct for this defect, are not subject to the same limitation, which is part of why the clustering pattern identified in the Middlehurst and Moore catalog, built predominantly from pre-modern equipment, deserves at least some adjustment for this known source of systematic observational error, even though it does not come close to explaining away the entire catalog. Particularly not the 20th century reports made using corrected optics, nor the independently corroborating radon data collected decades later by an entirely different measurement method that has nothing to do with any telescope's optical properties at all. Aristarchus crater, the same feature Herschel singled out in the 1780s, has gone on to become, by a wide margin, the most frequently reported location for transient lunar phenomena across the entire subsequent observational record, a pattern documented most comprehensively in a 1968 NASA technical report titled The Chronological Catalog of Reported Lunar Events, compiled by astronomers Barbara Middlehurst and Patrick Moore. That catalog assembled 579 separate reported TLP observations spanning from 1540 through 1967, drawn from historical astronomical literature, observatory logs, and amateur observation records, and cross-referenced them by location, date, and description. The catalog's most striking finding was not simply that TLP had been reported repeatedly, which was already generally known within the astronomical community, but that the reports clustered overwhelmingly around a small handful of specific lunar locations, with Aristarchus alone accounting for a disproportionate share of the total, followed by other recurring hotspots including the crater Plato, the crater Alphonsus, and the region around Grimaldi, rather than being distributed randomly across the lunar surface the way you would expect from simple observer error, atmospheric distortion, or misidentified meteor flashes, none of which have any obvious reason to favor one small patch of lunar geography over another. That non-random clustering is, in the view of the scientists who have taken TLP seriously as a genuine phenomenon rather than dismissing the entire catalog as observational noise, the single strongest argument for treating at least some fraction of the historical reports as real and physically meaningful rather than illusory. And the clustering deserves to be taken seriously because it did not stop being reported once professional astronomy moved into the 20th century and beyond. Soviet astronomer Nikolai Kozyrev, working at the Crimean Astrophysical Observatory, reported in November 1958 that he had captured spectroscopic evidence, not just a visual impression, but an actual recorded light spectrum of gas emission from the crater Alphonsus, interpreting the reddish glow he observed as consistent with fluorescing carbon-based gas venting from beneath the surface. Kozyrev's claim was controversial within the astronomical community at the time, and remains debated today regarding exactly what his spectrograph captured, but it represented one of the first attempts to move TLP observation beyond subjective visual description into the realm of instrumented, quantifiable measurement, and it directly influenced how seriously NASA itself would go on to treat the phenomenon once the Apollo program began sending astronauts to the moon directly. Kozyrev's 1958 claim deserves a fuller account than a single mention, because the controversy surrounding it illustrates the broader pattern of scientific caution and institutional skepticism that has shaped how TLP research has been received throughout its history. Kozyrev presented his spectrogram, showing what he interpreted as emission lines consistent with molecular carbon and possibly cyanogen gas venting from the central peak of Alphonsus to the International Astronomical Union, where it drew immediate and pointed criticism from other spectroscopists who argued that the instrument and exposure conditions Kozyrev used were prone to producing spurious emission-like artifacts, particularly given the technical challenges of obtaining a clean spectrogram of a faint, transient event against the overwhelming background brightness of the surrounding illuminated lunar surface. Kozyrev maintained the validity of his observation for the rest of his career, and no one has ever definitively proven the spectrogram to be an instrumental artifact rather than a genuine detection, but the scientific community's verdict on the claim has remained, in the decades since, one of unresolved skepticism rather than either acceptance or outright rejection, a state of affairs that mirrors the broader status of TLP research as a whole. Neither dismissed nor confirmed, simply left in an uncomfortable, underfunded scientific limbo for the better part of the past 70 years. TLP observation did not end with the close of the Apollo program, and it has not been left entirely to historical archives in the decades since, beginning in the 1980s and continuing in a more organized form after amateur astronomy software and networked reporting tools became widely available in the 1990s and 2000s. Dedicated volunteer observation networks, including one long coordinated through the Association of Lunar and Planetary Observers, have continued systematically monitoring known TLP hotspots and logging new reports using standardized reporting criteria intended to filter out likely instrumental or atmospheric artifacts before they enter the record. These modern networks benefit from equipment Herschel or even Kozyrev could scarcely have imagined, including digital imaging sensors capable of recording faint transient events with a level of objective, reviewable documentation no purely visual historical account could match, and video-based monitoring capable of capturing an event's precise duration and brightness curve rather than relying on an observer's memory and verbal description after the fact. That modern monitoring has continued to produce occasional reports from the same small cluster of historically active sites, Aristarchus chief among them, keeping the phenomenon under active, if still comparatively under-resourced, observation right up to the present day. That seriousness showed up explicitly in mission planning. NASA briefed the Apollo astronauts specifically on the history of TLP reports at Aristarchus before several missions, and the concern was not purely academic. During Apollo 11's approach to lunar orbit in July 1969, Command Module pilot Michael Collins radioed Mission Control to report that he could see an unusually bright, distinctly visible glow in the vicinity of Aristarchus, even before the spacecraft had fully adjusted to viewing the dark portion of the lunar surface. An observation that made it into the mission's official transcript, and that mission scientists at the time treated as a live, in-progress TLP event, rather than dismissing outright, given the extensive prior documentation already associated with that specific crater. Later, Apollo missions carried out deliberate observation campaigns from lunar orbit specifically targeting known TLP hotspots during the portions of each mission when astronauts had downtime and a clear view of the relevant terrain, part of a broader NASA effort during the Apollo era to determine definitively whether the phenomenon reflected something real happening on the lunar surface or something explainable purely in terms of Earth-based observational error. The modern scientific understanding of what likely causes at least some genuine TLP events has converged around a mechanism called outgassing, and it is a mechanism with real, direct instrumental support rather than being pure theoretical speculation. The Moon, despite its reputation as a completely inert, dead world, is not entirely free of internal gas release. Small quantities of gas, including radioactive radon and its decay products, are believed to migrate slowly upward from deep within the lunar interior along pre-existing fractures and fault lines, eventually escaping into the near vacuum above the surface in brief, localized venting events. NASA's Lunar Prospector mission, which orbited the Moon between 1998 and 1999, carrying an alpha particle spectrometer specifically designed to detect exactly this kind of radioactive decay signature, identified statistically significant radon-222 releases concentrated at several specific surface locations, and a number of those locations, including the region around Aristarchus, correspond closely to the same sites that dominate the centuries-long historical TLP catalog compiled by Middlehurst and Moore. This overlap between an independently measured, purely instrumental gas release signature and a centuries-old catalog built entirely from human visual observation is one of the more genuinely compelling pieces of corroborating evidence in this entire series, because the two datasets were collected using completely different methods, separated by decades, with no way for either to have influenced or contaminated the other. The proposed physical mechanism connecting that outgassing to visible light is still an active area of study, but the leading candidate involves a phenomenon called the piezoelectric effect, in which certain crystalline minerals generate a measurable electric charge when subjected to mechanical stress, such as the compression and shifting caused by the tidal flexing discussed several parts back in connection with deep moonquakes. Under this model, tidal stress fractures rock along existing fault lines, releasing trapped gas in the same moment that the mechanical stress on surrounding crystalline minerals generates a brief electrical discharge, potentially exciting the escaping gas to fluoresce or spark in a way that would be visible from Earth as exactly the kind of brief glow or flash reported at Aristarchus, Plato, and Alphonsus across 4 centuries of observation. A 2006 study conducted using data from NASA's own lunar orbital missions found a statistically meaningful correlation between the timing of historical TLP reports and periods of peak tidal stress on the lunar crust, adding further indirect support to a mechanism that ties outgassing, piezoelectric discharge, and the Moon's own orbital mechanics together into a single, internally consistent, entirely natural explanation, requiring no artificial activity of any kind to account for the pattern. It would be a disservice to this subject, however, to present the outgassing explanation as though it has fully and completely closed the case, because it has not. And mainstream planetary scientists working directly on TLP research are generally careful to say so themselves. A meaningful fraction of the historical catalog remains genuinely unexplained even under the outgassing model, including reports describing colors, durations, and visual characteristics that do not obviously map onto what a brief release of fluorescing gas should produce, and including a persistent minority of reports from skilled, credible observers describing phenomena that sound less like a localized glow and more like distinct points of light moving or blinking in a manner that resists easy explanation through either outgassing or simple observer error. It is this smaller, harder to explain residue within the broader TLP catalog that continues to draw attention from researchers exploring the observation station hypothesis, who point out that a civilization maintaining any kind of active presence on or beneath the lunar surface, whether an outpost, sensor array, or something else entirely, might reasonably be expected to produce exactly the kind of localized, occasionally repeating light signatures that dominate the historical record, clustered at a small number of specific sites rather than scattered randomly, in a way that coincidentally overlaps with, but is not necessarily fully explained by, the natural gas venting locations independently identified by instruments like Lunar Prospector's spectrometer. It is worth being precise here about what separates confirmed lunar light events from the more ambiguous historical TLP catalog, because conflating the two does a disservice to both. Since the mid-2000s, NASA has operated a dedicated lunar impact monitoring program using automated telescopes to watch the moon's dark hemisphere continuously for brief flashes caused by meteoroids striking the surface at high velocity, a phenomenon entirely separate from the outgassing-based TLP discussion, and one that is thoroughly, unambiguously understood, cataloged in the hundreds of confirmed events since the program began, each one consistent in brightness, duration, and behavior, with a small, fast-moving object striking bare rock and releasing its kinetic energy as a brief flash of light and heat. These confirmed impact flashes are distributed relatively randomly across the lunar surface, following the same broad statistical pattern you would expect from randomly arriving space debris, and they are not the source of the clustering pattern that makes the older TLP catalog so interesting. The two phenomena, confirmed random impact flashes and clustered, recurring, non-impact glows concentrated at specific named craters, are genuinely distinct categories of lunar light event, and any account of this subject that blurs them together in either direction, whether inflating ordinary impact flashes into evidence of something stranger or waving away the clustered TLP pattern as nothing more than misidentified impacts, is not representing the actual state of the evidence accurately. It is worth being precise here about what separates confirmed lunar light events from the more ambiguous historical TLP catalog, because conflating the two does a disservice to both. Since the mid-2000s, NASA has operated a dedicated lunar impact monitoring program using automated telescopes to watch the moon's dark hemisphere continuously for brief flashes caused by meteoroids striking the surface at high velocity, a phenomenon entirely separate from the outgassing-based TLP discussion and one that is thoroughly, unambiguously understood, cataloged in the hundreds of confirmed events since the program began, each one consistent in brightness, duration, and behavior, with a small, fast-moving object striking bare rock and releasing its kinetic energy as a brief flash of light and heat. These confirmed impact flashes are distributed relatively randomly across the lunar surface, following the same broad statistical pattern you would expect from randomly arriving space debris, and they are not the source of the clustering pattern that makes the older TLP catalog so interesting. The two phenomena, confirmed random impact flashes and clustered recurring non-impact glows concentrated at specific named craters, are genuinely distinct categories of lunar light event, and any account of this subject that blurs them together in either direction, whether inflating ordinary impact flashes into evidence of something stranger or waving away the clustered TLP pattern as nothing more than misidentified impacts, is not representing the actual state of the evidence accurately. Grimaldi and Plato, the two other consistently named hotspots in the Middlehurst and Moore catalog, alongside Aristarchus and Alphonsus, each carry their own distinct observational character worth noting briefly. Plato, A large, dark-floored crater near the moon's northern limb has been repeatedly described across multiple centuries of reports as exhibiting small, temporary bright spots on its otherwise uniformly dark floor, visible for periods ranging from minutes to hours before fading back into the surrounding darkness, a pattern distinct from the reddish glows more commonly associated with Aristarchus. Grimaldi, a vast, ancient impact basin near the moon's western limb, has instead generated a smaller number of reports, but ones that skew toward comparatively long-duration dimming or darkening events rather than brightening, observers across different eras describing the floor of the basin appearing to lose contrast or detail temporarily, in a manner some have likened to a thin mist or haze passing across an airless world that, by every conventional understanding of lunar physics, should be incapable of hosting anything resembling mist or haze at all. Whether that specific class of report reflects genuine surface obscuration through some kind of transient dust or gas suspension, an atmospheric effect on the Earth-based observer's side of the equation, or something else entirely, remains one of the least satisfactorily explained subcategories within the broader TLP catalog, a detail worth flagging honestly rather than folding it into the same outgassing and glow framework that fits the Aristarchus reports more comfortably. Where that leaves us, honestly, is with a phenomenon that occupies a genuinely unusual middle ground in this series, not fully explained, but not remotely unexplored either, actively studied by mainstream planetary scientists using real instruments, with a leading natural hypothesis, outgassing triggered by tidal stress and expressed through piezoelectric discharge, that fits a meaningful portion of the data reasonably well, while leaving a smaller residue of specific historical reports resistant to easy explanation under any model, natural or otherwise. That residue is not, on its own, proof of anything, but it is a genuine, acknowledged, published gap in our understanding of what is actually happening at a handful of very specific locations on the lunar surface, gathered from 9 centuries of human observation, corroborated in part by modern instrumented spectroscopy, and never fully resolved by any single explanation offered so far. The anomalous archive. Beyond lights and seismographs sits the most visually persuasive category of evidence this hypothesis has ever produced: photographs. NASA's Lunar Orbiter program, flown between 1966 and 1967 to scout landing sites, returned tens of thousands of frames, and one image from Lunar Orbiter 2 became an instant sensation. In it, a tall, narrow shadow rises from the sinus medii region, cast by an object taller than it is wide. Aerospace engineer William Blair, examining the frame for Boeing, calculated the shadow implied a spire roughly 40 feet tall, and the press nicknamed the objects the Blair Cuspids. Later, higher resolution imaging from Lunar Orbiter 5 and eventually the modern Lunar Reconnaissance Orbiter resolved the same terrain and found ordinary boulders and low hills, their long, distorted shadows, an artifact of the extremely low sun angle at which the original frame was taken, a lighting condition that can stretch a 3-foot rock into a shadow 40 feet long, the same optical effect that makes a person's shadow stretch across an entire field at sunset. A second recurring claim involves retouching marks, faint airbrushed lines visible on some original Apollo-era prints, which turn out to be a mundane feature of 1960s photo processing, where technicians manually brightened or blocked out overexposed sections and lens flare before publication, a process since documented in NASA's own archival notes and confirmed by comparing the retouched prints against the original, unretouched negatives, which show no trace of the disputed lines. A third category involves gaps in NASA's own photographic numbering system, frame numbers that appear to skip in the public archive, cited by some researchers as evidence of deliberate removal. Archivists who have examined the cataloging system directly attribute the great majority of these gaps to routine mission planning, frames reserved for calibration exposures, test shots, or sequences that were never actually taken, rather than images removed after the fact, though a small number of individual frame gaps remain genuinely unaccounted for in the public record, even after archival review. It is worth adding one further wrinkle here. The Lunar Orbiter program's original data was recorded on analog tape using a now obsolete format, and by the early 2000s, the tapes themselves, along with the specialized drives needed to read them, were at real risk of becoming permanently unreadable. A dedicated volunteer effort called the Lunar Orbiter Image Recovery Project, working out of a decommissioned McDonald's building at NASA's Ames Research Center between 2007 and 2014, painstakingly restored the original drive hardware and digitized the full archive at far higher fidelity than the printed images the public had relied on for decades, incidentally resolving several older anomaly claims simply by providing a cleaner source image than had ever been publicly available before. That project is worth dwelling on for a moment because it is a genuinely good faith illustration of how this entire subject tends to actually get resolved in practice, not through official denial or dramatic revelation, but through patient, often underfunded, often volunteer-driven technical work, run by people motivated primarily by archival preservation rather than by any interest in proving or disproving anomaly claims one way or the other, whose incidental byproduct was simply better data. Nearly every specific structure claim from the original Orbiter and Apollo archive that has since been re-imaged at higher resolution has resolved into ordinary geology, though the sheer size of the total archive, well over 1 million frames across all lunar missions combined, means new claims continue to surface faster than they can be individually re-examined. The far side. Because the moon is tidally locked, humanity saw the far hemisphere for the first time only in 1959, when the Soviet probe Luna 3 transmitted grainy images back to Earth. What those images and every mission since have confirmed is a genuinely strange asymmetry. The far side is almost entirely highland terrain, pale, ancient, and heavily cratered, with only a scattering of small, dark maria compared to the near side's broad volcanic plains. Some researchers have asked why, if the moon is an installation, its far side would be the more heavily fortified, crater-dense hemisphere, permanently turned away from Earth's view, functioning almost as a shielded or hidden face. Others take the opposite reading, arguing that a permanently Earth-hidden hemisphere is exactly where an observing or monitoring installation would be placed if concealment from the observed planet were a priority. Mainstream geophysics sets aside both readings and answers with crustal thickness. Grail gravity mapping shows the far side crust is, in places, more than twice as thick as the near sides, likely because more heat-producing radioactive material concentrated in the near side mantle early in lunar history, and possibly because of a second, smaller impact shortly after the moon formed. A big splat that piled extra material onto the far side. A thicker crust made it far harder for interior magma to break through and form maria, which is why the far side, despite being just as old and just as heavily bombarded as the near side, shows so much less volcanic resurfacing. This asymmetry was itself once treated as anomalous enough to warrant its own explanatory theories well outside the mainstream, before Grail's 2011 gravity data gave researchers the crustal thickness measurements needed to actually test those competing explanations against real numbers rather than speculation, a pattern that recurs throughout this entire subject. Genuine unexplained asymmetry, decades of competing theories filling the gap, and eventual resolution once an instrument capable of actually measuring the relevant physical quantity finally flew. China's Chang'e 4 mission made the first ever landing on the far side in January 2019 inside the South Pole Aitken Basin, the oldest and deepest impact basin known in the solar system, and continues returning data that supports the crustal asymmetry explanation over any alternative, including mineral readings from its Yutu-2 rover, consistent with deep mantle material excavated by the ancient basin-forming impact, rather than any indication of artificial excavation or construction. Communicating with a lander on the far side requires its own workaround, since the bulk of the moon itself blocks any direct radio line to Earth, and China solved the problem by launching a dedicated relay satellite, Queqiao, into a stable position beyond the moon that keeps both the far side lander and Earth in view simultaneously, a logistical detail worth mentioning because it is sometimes inaccurately folded into secrecy. Claims about the far side being intentionally difficult to monitor when the difficulty is simple geometry, not concealment. Testimony. No Apollo mission transcript documents an astronaut reporting an artificial structure on the surface. The record of what was actually said in real time during 6 landings is free of that specific claim. What fuels this part of the theory instead are statements made later, off-mission, by a handful of astronauts. Edgar Mitchell, the 6th man to walk on the moon, spent much of his post-NASA life as a vocal proponent of the idea that Earth has been visited by extraterrestrial intelligence, founding an institute devoted to consciousness research and speaking publicly for decades about his conviction that governments were withholding evidence of contact, though his claims centered on alleged Earth-based incidents and Roswell-adjacent government secrecy, rather than anything he personally observed on the lunar surface. Buzz Aldrin has spoken publicly many times about an unusual object he and his crewmates observed during the Apollo 11 outbound flight, later concluded by NASA analysts to almost certainly have been a jettisoned panel from their own spacecraft reflecting sunlight, an explanation Aldrin himself has generally accepted while still describing the sighting as genuinely unidentified in the moment it occurred. Other astronauts, including several who never made public UFO-related statements at all, have nonetheless been quoted, misquoted, or paraphrased across decades of documentary and internet content in ways that blur their actual public record, a pattern that makes tracing any specific claim back to its original verifiable source an essential and often frustrating exercise for anyone trying to evaluate this category of evidence honestly. Gordon Cooper, a Mercury and Gemini-era astronaut who never flew to the moon himself, but whose broader public statements about UFOs are frequently folded into lunar anomaly discussions regardless, is a useful example of exactly this blurring. His stated beliefs concerned unexplained aerial phenomena and alleged government cover-ups generally, not specific lunar observations, yet his name recurs constantly in lunar anomaly compilations as though his testimony bore directly on the moon itself. Separating what a given astronaut actually said, on the record, from what later compilations have attributed to them requires returning to primary sources, oral history archives, recorded interviews, published memoirs, rather than relying on the secondhand summaries that dominate most popular treatments of this subject. The honest through line is this: on-mission, real-time testimony, recorded on the spot and preserved in official transcripts, contains no reports of artificial lunar structures. The more suggestive statements come later, filtered through interviews, books, and personal belief systems formed well after the missions ended, which is a separate matter entirely from what was actually recorded on the surface in the moment. It is also worth noting that several astronauts, including Neil Armstrong himself, were famously reluctant to engage with UFO or ancient astronaut speculation in public throughout their post-NASA lives, a reticence that popular treatments of this subject often simply skip past in favor of the more talkative minority, creating a skewed impression of the astronaut corps as a whole, leaning toward belief in lunar anomalies when the actual public record is considerably more mixed, with the most famous and vocal claims concentrated in a small handful of individuals, rather than reflecting anything like a consensus among the 12 men who actually walked on the surface. Geometry and the monolith claims. The most persistent geometric claims trace to researcher Richard Hoagland, whose Enterprise mission organization spent decades analyzing lunar orbiter and Apollo imagery for signs of glass towers, domes, and ruined structures, particularly in the Sinus Medii region already discussed in the previous part on photography. Hoagland's arguments typically layer geometric analysis on top of the raw images, drawing lines between claimed structural edges and calculating angles he argues are too regular to be natural. Imaging specialists who have reviewed the same frames, including analysts contracted by NASA itself, attribute the claimed geometry to scanline artifacts from the process used to transmit and reconstruct 1960s-era images, dust and emulsion flaws on the original film, and simple pareidolia, the same perceptual tendency that finds faces in wood grain applied to grainy, low-resolution frames stretched and contrast-enhanced well beyond their original data quality. A process that can manufacture the appearance of straight edges and regular angles out of what is actually random noise once an image is pushed far enough past its native resolution. No claimed geometric anomaly from this body of imagery has been independently confirmed once the same terrain was rephotographed at the vastly higher resolution the Lunar Reconnaissance Orbiter has provided since 2009, a resolution fine enough to distinguish individual astronaut bootprints at the Apollo landing sites, and by that same standard, capable of resolving genuine artificial geometry had any actually been present at the claimed locations. A related and more recent claim, circulated widely online beginning in the 2010s, involves supposed structural anomalies visible in Google Moon and Google Earth's lunar imaging layers, screenshots of oddly regular shading or linear artifacts presented as evidence of buried installations. Google's lunar imagery layer is compiled from a mosaic of source images from multiple missions and eras, stitched together with automated blending algorithms, and the seams between source images, along with compression artifacts introduced by the tiling and rendering process used to serve the imagery at different zoom levels, reliably produce exactly the kind of geometric-looking regularity these claims point to, without any of it reflecting the actual lunar surface at all, a mapping software artifact rather than a discovery. A suspiciously perfect orbit. Return to the eclipse coincidence from the first part of this series. The moon's size and distance combine to make it appear almost exactly the same size as the sun from Earth's surface, a fit found nowhere else we've observed in the solar system. Proponents of design treat the odds of that coincidence as vanishingly small, sometimes extending the argument to the moon's role in stabilizing Earth's axial tilt and its influence on tides, framing the entire package as too fortuitous and too favorable to the emergence of complex life to be accidental. The mainstream answer rests on 2 points. First, the moon is drifting away from Earth by about 1.5 inches a year, meaning this precise eclipse fit is a temporary condition, true for only a narrow slice of Earth's multi-billion-year history, not a fixed engineered constant, which undercuts the idea of deliberate long-term design. A civilization capable of engineering such a coincidence would presumably have engineered it to last, rather than leaving it to drift out of alignment within a few 100 million years, an eye blink on a 4.5 billion year timeline. Second, this is a selection effect. Across billions of star systems, some fraction will contain a moon-planet star geometry that happens to produce a close eclipse fit, and only the observers who exist in that fraction, at the specific moment in that system's history when the fit holds, are positioned to marvel at it. The same logic that explains why we find ourselves on a planet hospitable to life rather than a hostile one, without requiring anyone to have built it that way. There is a third point worth adding, one less commonly raised but worth including for completeness. The coincidence itself is really a coincidence of 2 separate ratios lining up, the sun-to-moon size ratio and the sun-to-moon distance ratio. And while it is true that no other observed exomoon system has been confirmed to share this specific alignment, our ability to detect and characterize moons around planets outside our solar system remains extremely limited, even with modern telescopes. Meaning the claim that Earth's eclipse geometry is unique in the universe is, strictly speaking, an argument from absence of data rather than a confirmed astronomical rarity, a distinction worth holding on to given how often the uniqueness of the eclipse fit gets stated as though it were an established statistical fact rather than a currently unverifiable one. Parallel claims, Soviet and Chinese missions. The Soviet Luna program achieved its own list of firsts, including Luna 9's first soft landing in 1966, and Soviet scientists worked from largely the same raw data as their American counterparts, reaching broadly similar conclusions about lunar geology despite Cold War secrecy limiting direct collaboration between the 2 programs for most of the space race. Claims that the Soviets suppressed anomalous findings remain undocumented. The secrecy that did exist mirrored ordinary Cold War military classification of rocket and guidance technology, not evidence of hidden geological discoveries, and Soviet planetary scientists who later collaborated openly with Western counterparts after the Cold War's end brought no undisclosed anomalies with them. It is worth noting that the Soviet Union's Luna program was not without its own well-documented failures and setbacks. including numerous unsuccessful launches and lost spacecraft that were, at the time, kept quiet or downplayed in official Soviet state media, a genuine pattern of secrecy, but one motivated by the political embarrassment of program failures rather than by any suppressed scientific discovery, a distinction that matters because it illustrates the more mundane, more human motivations, national pride, avoiding embarrassment, standard military classification, that actually drove Cold War-era lunar secrecy, as opposed to the more dramatic motivations sometimes attributed to it in retrospect. China's more recent Chang'e program produced the closest thing to a modern viral anomaly. In 2019, the U-22 rover's onboard camera photographed a cube-shaped object on the horizon during its far-side traverse, quickly dubbed the Mystery Hut or Mystery Cube across Chinese and international media, generating weeks of speculation before the rover could travel close enough for a clear look. When it did, roughly 2 months later, Chinese mission scientists identified it in their own 2022 published account as an oddly shaped boulder. Its rectangular silhouette an effect of distance, low-resolution imaging, and lighting angle rather than construction, a resolved case that illustrates how quickly apparent anomalies can dissolve once better-positioned data becomes available, and a useful reminder that the same pattern, distant, ambiguous image followed by mundane resolution once better data arrives, recurs constantly throughout this entire subject's history. India's Chandrayaan program, though not a crude effort and not the subject of significant anomaly claims of its own, deserves a brief mention here for a different reason. Its 2023 Chandrayaan-3 landing near the lunar South Pole and the water ice mapping data returned by its predecessor Chandrayaan-1 in 2009 represent exactly the kind of independent, multinational verification this series has emphasized throughout. Additional space agencies, using their own instruments, converging on the same basic geological picture rather than surfacing evidence of anything hidden. Secrecy and the Cold War frame. Real, documented lapses have given secrecy claims genuine fuel. NASA admitted in 2006 that the original high-quality slow-scan telemetry tapes of the Apollo 11 moonwalk, the best quality source footage that ever existed, had been lost, most likely erased and reused during a period of tape shortages in the 1970s and 80s. A mundane bureaucratic failure that nonetheless left the single most important video record in spaceflight history permanently degraded, reconstructed, since only from lower quality broadcast copies. Combine that with routine Cold War-era classification of reconnaissance satellite-derived data, some of which shared imaging technology with early lunar mapping programs, and with the ordinary redactions that appear in any government document released under Freedom of Information requests, redactions that in most confirmed cases turn out to protect unrelated personnel information, proprietary contractor data, or genuinely unrelated national security material rather than lunar findings, and you get an environment where genuine institutional carelessness and genuine unrelated national security secrecy have repeatedly been read by a public primed by decades of real government deception on other subjects, from Watergate to later declassified Cold War programs, as evidence of something being hidden specifically about the moon. That reading is understandable given the historical pattern of real institutional secrecy elsewhere. It is not, however, supported by any confirmed case of a lunar-specific finding having been the actual target of a documented redaction or classification decision. It is also worth noting that the single largest source of primary Apollo-era documentation, mission transcripts, technical reports, sample analyses, and photographic archives has been progressively declassified and made freely available online since the 1990s, including material that was originally restricted for reasons entirely unrelated to lunar geology, such as details of guidance and propulsion systems with clear Cold War military applications. The fact that so much of this archive is now open, searchable, and has been independently cross-checked by researchers, historians, and enthusiasts worldwide for decades without producing a confirmed lunar anomaly, makes the ongoing secrecy narrative progressively harder to sustain with each passing year of continued access. Building the observation station case. Assembled at its strongest, the case runs like this. A moon disproportionately large for its planet, positioned with an exact eclipse fit that no other observed system shares, seismically ringing in a way not fully replicated on any other body we've measured, its low density and mascons debated since before Apollo ever landed, its historical light flash reports clustering non-randomly at a handful of sites that later instruments confirmed vent real gas, its far side thick-crusted and comparatively unexplored, its astronaut record containing both official silence and, later, unofficial belief, all sitting atop a space program that was born from military rivalry, cloaked in real secrecy, and ended abruptly after 6 landings with no return for 50 years. Add to that the ancient mythological record's persistent, cross-cultural framing of the moon as an object that arrived, watched, or was placed, and the giant impact hypothesis's own unresolved isotopic crisis, and the case, stated this way, without the individual rebuttals attached, reads as more than coincidence to those inclined to see it that way. A proponent assembling this case would also point to the sheer improbability of any single body checking this many boxes at once, arguing that while each individual anomaly might plausibly be explained away in isolation, the cumulative weight of so many partial mysteries clustering around one specific object, rather than being spread evenly and randomly across the many other moons, planets, and asteroids we have studied in comparable detail, is itself a data point worth taking seriously. A statistical argument about clustering rather than a claim resting on any single piece of evidence alone. This is the Steelman version, deliberately built to be as persuasive as the honest evidence allows, and it deserves to be stated in full before the counter-argument gets its turn. It is worth being clear about what this Steelman does and does not claim. It does not claim proof. It claims a pattern of unresolved specifics, clustered densely enough across enough independent categories of evidence, seismic, gravitational, photographic, mythological, historical, and testimonial, that dismissing the entire pattern with a single wave of the hand feels, to a careful observer, like it requires almost as much confidence as accepting it outright. Holding that tension between a pattern real enough to earn genuine attention and a body of individual claims that mostly do not survive close examination is the position this series has tried to occupy throughout. The skeptical rebuttal. Laid back against that same list, nearly every individual claim carries a specific, evidenced counter. The seismic ringing is explained by dry, fractured megaregolith scattering, a mechanism confirmed by comparison against Mars's own, less extreme seismic behavior. The density and the mascons are explained by a small core and thick anorthosite crust, confirmed by decades of gravity mapping culminating in Grail, the moment of inertia measurement. One of the more decisive figures in this entire series actively argues against a hollow interior rather than merely failing to confirm one. The eclipse fit is a temporary, selection-biased coincidence undercut by the moon's own measured recession rate. The photographic structures resolve into boulders and scan artifacts under modern imaging fine enough to see astronaut boot prints. The far side's asymmetry has a specific, testable crustal explanation. No on-mission testimony reports artificial structures, only later personal statements made well outside the recorded mission record. And every space agency that has flown to the moon, American, Soviet, and Chinese, has published converging, mutually reinforcing geological data with no independently verified anomaly still standing once follow-up imaging or analysis has been applied. The scientific standard for extraordinary claims, that they require extraordinary evidence, has not yet been met by any single piece of this case, and the individually unresolved details that remain, mascon formation nuances beneath unfilled craters, shallow moonquake specifics, a residue of TLP reports that outgassing alone doesn't fully account for, are exactly the kind of loose threads any actively studied natural body leaves behind. not a coordinated signature of concealment. It is worth adding a broader methodological point here, because it applies to this entire case and not just its individual pieces. Peer review and independent replication, the two processes that have resolved essentially every genuine anomaly discussed across this series, from the fault scarps to the Mascon mechanics to the U22 boulder, function precisely because they are slow, distributed, and skeptical by design, unlike the far faster, far less accountable process by which a single striking photograph or a single dramatic claim can spread across millions of viewers before anyone has had the chance to check it against better data. That asymmetry between how quickly a claim can spread and how slowly it can be properly checked is not evidence of a cover-up. It is simply a mismatch in speed between two very different processes, one built for attention and one built for accuracy, and mistaking the lag between them for suppression is one of the most consistent errors running through the entire history of this hypothesis. The open question, what endures after all of that, is not a proof but a habit of attention, the same habit that put a moon god at the center of Bronze Age Mesopotamia and sent 3 men to its surface in a 15-story rocket less than 4 centuries after Galileo first turned a telescope on it. The moon keeps a small number of genuine, published, scientist-acknowledged puzzles open even now: Mascon formation, the fine mechanics of TLP, the details of its earliest hours after the Theia impact, and it is that narrow, honest gap between what is known and what is fully explained that the observation station hypothesis has always lived inside, not because the evidence demands it, but because the gap has never quite closed, and every generation that looks up finds a fresh reason to wonder whether it might. Future missions, Artemis among them, will land humans back on the surface for the first time in over 50 years, equipped with instruments the Apollo era could not have imagined. And whatever they find will either close that gap for good or simply relocate it to some smaller, stranger corner of the data. That is the only honest answer this series can offer. It is worth remembering, too, that this same open, unfinished quality is what makes the moon worth returning to at all, scientifically as well as culturally. A fully solved object generates textbooks, but a partially solved one generates missions, funding, and the kind of sustained human curiosity that put footprints in its dust in the first place and will, within the coming decade, put them there again. Across these 17 parts, the through line has not been that the moon is hiding something, nor that every mainstream explanation is beyond question, but that both of those simpler stories are more comfortable than the truth. A genuinely strange object, mostly explained, partially not, orbiting a planet whose inhabitants have never quite been able to look at it and see only a rock. The moon is still up there tonight, exactly where it has always been, pulling the tides, catching the sunlight, keeping the same face turned toward us that it always has. And it is still, after everything we now know, not entirely finished explaining itself. Thanks for watching, everyone. If you enjoyed this video, don't forget to like, subscribe, and hit that notification bell so you never miss an update. Drop a comment below with your thoughts. I love hearing from you. Check out more videos on the screen, and I'll see you in the next one. Take care.